Audio review of textbook for Class 12. Physics Part 1. Chapter 1. Electric Charges and Fields.
Okay, so for today's deep dive, we are going to be looking at electrostatics.
Yeah, so that's the study of forces, fields, and potentials arising from static charges.
Right, and by static, we mean charges that are not moving or changing with time.
Exactly. They're just kind of hanging out, being stationary.
And I think most people have some experience with static electricity. You know, like when you take off a synthetic sweater on a dry day and you hear that crackling sound.
Oh, yeah, or when you get a shock from touching a doorknob or something.
Right, those are all examples of electrostatics in action.
It's pretty amazing to think that these everyday little annoyances are actually governed by some pretty fundamental principles of physics.
So let's start with a bit of history. Where did this whole idea of electrostatics even come from?
Well, it all goes back to ancient Greece, around 600 BC.
Okay, so way back.
Yeah, there was this philosopher named Thales of Miletus.
Thales.
Yeah, and he was messing around with amber, which is that fossilized tree sap.
Oh, okay, I've seen that stuff.
Yeah, so he noticed that when he rubbed amber with wool or silk, it would start to attract small light objects like bits of fluff or paper.
Like magic.
Kinda, yeah. It was one of the earliest recorded observations of what we now call static electricity.
And it's interesting because the word electricity actually comes from the Greek word for amber, which is electron.
That's right. So our entire understanding of this fundamental force of nature stems from a sticky piece of ancient tree resin.
Pretty wild, huh?
It is. And over time, people discovered that it wasn't just amber that could do this.
Right.
They found that many different materials could be made to attract light objects when rubbed together.
So like a whole new world of weird attractions.
Exactly. And it wasn't just attraction either. Sometimes the objects would actually repel each other.
Oh, so they were like playing hard to get?
Right. So through a lot of careful experimentation, people started to figure out some basic patterns.
Patterns like?
Well, they noticed that when you rubbed two glass rods with silk and brought them close together, they would repel each other. Same thing if you rubbed two plastic rods with fur.
Repulsion City.
Exactly. But if you brought a silk-rubbed glass rod near a fur-rubbed plastic rod, they would attract.
Interesting. So it seemed like there were two different types of electric charge.
That's right. And we now call this property polarity.
Polarity.
So it's not just about whether an object has charge or not, it's about what kind of charge it has.
So there's like positive and negative.
Exactly. And we can thank Benjamin Franklin for coming up with that naming convention.
Ah, Ben Franklin, the kite guy.
Yeah, well, he did a lot more than just fly a kite in a thunderstorm.
Right.
He made significant contributions to our understanding of electricity.
Okay, so what did he do specifically?
Well, he was the one who proposed that there were two types of electric charge, and he arbitrarily called them positive and negative.
Arbitrarily.
Yeah, he could have easily called them black and white or up and down.
Right. I guess it doesn't really matter what you call them as long as you're consistent.
Exactly, and the convention we use today is that the charge on a glass rod after being rubbed with silk is positive,
Okay.
and the charge on a plastic rod after being rubbed with fur is negative.
So that's how we define positive and negative.
Yeah. And if an object has a net charge, we say it's electrified or charged.
Right.
And if the positive and negative charges balance out, we say it's electrically neutral.
Okay. Makes sense.
Now, how do we actually detect these charges?
Yeah. How do we know if something is charged or not?
Well, one way is to use a device called a gold leaf electroscope.
Gold leaf electroscope.
Yeah, it's a pretty simple device, basically. It consists of a metal rod with a couple of very thin gold leaves attached to the bottom.
Gold leaves, huh?
Yeah, and it's all enclosed in a glass case to protect the delicate leaves.
Okay. So how does it work?
Well, if you bring a charged object near the metal knob at the top of the electroscope, the charge will induce a separation of charge in the metal rod.
Induced separation.
Yeah, meaning some of the charges will be pushed down into the gold leaves. And since the leaves now have the same charge, they will repel each other and spread apart.
So the more charge there is, the farther apart the leaves will spread.
Exactly. It's a pretty sensitive way to detect the presence and even the relative amount of charge.
So it's like a tiny gold leaf dance party for charges.
Yeah, kind of.
Okay, so we've talked about how to detect charges, but what about the fundamental question of Why do objects even get charged in the first place?
Ah, that's a great question. And to understand it, we need to zoom in to the level of atoms and molecules.
Right, the building blocks of everything.
Exactly. So as you know, all matter is made up of atoms,
Okay,
and each atom has a nucleus containing positively charged protons,
right.
and then whizzing around the nucleus are negatively charged electrons.
So in a neutral atom, the number of protons and electrons is equal.
Right. That's why the atom as a whole has no net charge.
Okay, but how does that explain how objects get charged?
Well, when you rub two objects together, you're essentially causing some of the electrons to be transferred from one object to the other.
Right. Oh, so it's like an electron swap meet.
Yeah, kind of. So the object that loses electrons becomes positively charged.
Right, because it now has more protons than electrons.
Exactly. And the object that gains electrons becomes negatively charged.
Okay, so it's all about the balance of protons and electrons.
And here's the amazing part. The forces that hold all of this matter together, the chemical bonds, the forces within the atoms themselves, even things like how glue sticks or why water forms droplets are all fundamentally electrical in nature.
Really, so electricity is not just this weird thing we observe when we rub balloons on our hair.
No, it's the very foundation of how the universe works.
That's pretty mind-blowing.
It is, and it all boils down to the interactions between these charged particles, the attractions and repulsions.
Okay, so we've got this basic picture of charge. Now let's talk about how different materials behave with respect to electric charge.
Yeah, we can classify materials into two main categories based on how easily they allow electric charge to flow through them.
Okay, so what are the categories?
Well, we have conductors.
Yeah.
And insulators.
Insulators, okay, so what's the difference?
Conductors are materials that allow electric charge to move through them very easily.
Okay, so they're like the express lanes for electrons.
Exactly. Metals like copper, aluminum, and silver are excellent conductors.
Right. I've heard that copper is used in electrical wiring.
That's right. It's very good at conducting electricity.
Okay, what about insulators?
Insulators are the opposite. They resist the flow of electric charge.
So they're like roadblocks for electrons.
Exactly. Materials like glass, rubber, and plastic are good insulators.
So that's why electrical wires are usually covered in plastic.
Right. The plastic insulation prevents the electric current from leaking out and keeps us safe.
Okay, so conductors let charge flow freely, insulators block it. And what about our own bodies? Are we conductors or insulators?
Well, our bodies are actually pretty good conductors thanks to the salty water and ions we contain.
Oh, so that's why we get a shock when we touch something charged.
Exactly. The charge can flow through our bodies quite easily.
Okay, makes sense.
And that's also why it's important to be careful around electricity.
Right. Don't want to become a human conductor.
Exactly. Now, let's talk a bit about how charge distributes itself on conductors and insulators.
Okay.
So if you place some excess charge on a conductor, the charges will repel each other and spread out as evenly as possible over the surface.
So it's like they're trying to get as far away from each other as possible.
Exactly. But on an insulator, the charges can't move freely.
Right.
So if you place some charge on an insulator, it will tend to stay localized in that area.
Okay, so that explains why you can rub a balloon on your hair and it will stick to the wall.
Exactly. The balloon becomes charged, and the charge stays on the surface of the balloon.
And then it attracts the opposite charges in the wall.
Right. And there's actually another category of materials called semiconductors.
Semiconductors, okay.
Yeah, they're kind of in between conductors and insulators.
In between.
Yeah, their conductivity can be controlled by things like temperature or impurities.
Oh, so they're like the adjustable wrenches of the electrical world.
Yeah, kind of. And semiconductors are incredibly important in modern electronics. They're the basis for things like computer chips and transistors.
Wow, so we've gone from ancient amber to the heart of modern technology.
That's right. Electrostatics is everywhere.
Okay, so we've got a good grasp of the basic concepts of charge conductors and insulators. Now, let's dig a little deeper into the properties of electric charge itself.
Yeah, let's get into the nitty-gritty details.
Okay, so we already know that there are two types of charge, positive and negative.
Right, and that, charges repel while opposite charges attract.
But what else is there to know?
Well, one important property is that charge is additive.
Additive.
Yeah, meaning if you have a bunch of charges together,
Yeah.
the total charge is just the sum of all the individual charges.
Okay, that makes sense. It's like adding apples and oranges.
Except with charges, you have to pay attention to the signs positive and negative.
Right, so if you have a positive charge and a negative charge of equal magnitude, they will cancel each other out?
Exactly, and the net charge will be 0.
Okay, what else?
Well, another fundamental property is that charge is conserved.
Conserved.
Yeah, meaning the total amount of charge in the universe is constant.
So you can't just create or destroy charge.
Exactly. Charge can be transferred from one object to another, but it can never be created or destroyed.
Oh, so it's like a cosmic game of musical chairs with electrons.
Yeah, kind of.
Yeah.
And this principle of charge conservation has been experimentally verified to an incredibly high degree of accuracy.
So it's a pretty solid law.
It is, and it's one of the cornerstones of modern physics.
Okay, what else is there to know about charge?
Well, the third important property is that charge is quantized.
Quantized, huh? That sounds fancy.
It just means that charge comes in discrete packets.
Packets.
Like you can't have half an electron.
Right.
The smallest unit of charge is the charge on a single electron or proton.
Okay, and what do we call this fundamental unit of charge?
We call it the elementary charge, and it's denoted by the letter E.
You okay?
And the value of E is about 1.6 times 10 to the minus 19 coulombs. Yeah, that's the standard unit of charge in the SI system.
Ooh, that's the International System of Units, right?
That's right. It's the most widely used system of units in science and engineering.
Okay, so the elementary charge is really tiny.
It is, but even though it's so small, it's still a fundamental constant of nature.
And all charges we observe are always integer multiples of this elementary charge.
Exactly. You can have 1e, 2e, 3e, and so on, but you'll never find a charge that's like 1.5e.
So it's like charge comes in these indivisible Lego bricks?
Yeah, that's a good way to think about it.
Okay, so we've talked about the properties of charge. Now, let's get into the juicy stuff. How do we actually quantify the force between charges?
That's where Coulomb's law comes in.
Coulomb's law. Okay.
Named after Charles-Augustin de Coulomb, a French physicist.
So what does Coulomb's law tell us?
Well, it tells us that the force between two-point charges is directly proportional to the product of their charges.
Okay.
And inversely proportional to the square of the distance between them.
So if you double the distance between the charges, the force will be 4 times weaker.
Exactly, and the force acts along the line connecting the charges.
So it's a central force like gravity.
That's right, and the mathematical expression for Coulomb's law is F equals K times the absolute value of Q1 times Q2 divided by R squared.
Okay, so F is the force, K is a constant Q1, and Q2 are the charges, and R is the distance.
Right, and the constant K is called Coulomb's constant, and it has a value of approximately 9 times 10 to the 9 Newton meters squared per Coulomb squared.
Wow, that's a big number.
It is, and that's because the Coulomb is actually a very large unit of charge.
So in practice, we often deal with smaller units like microcoulombs or nanocoulombs.
Right, those are more manageable.
And the absolute value signs in the equation are there because the force is always positive, whether the charges are positive or negative.
Exactly. It's just the magnitude of the force we're interested in here.
Okay. And how did Coulomb actually determine this law?
Well, he used a very sensitive instrument called a torsion balance.
Torsion balance?
Yeah, it's basically a rod suspended from a thin wire, and if you apply a force to the rod, it will twist the wire.
Oh, okay.
So Coulomb charged up 2 small spheres and measured the force between them by observing how much the wire twisted.
And he did this for different distances and charges.
That's right. And from his measurements, he was able to deduce the inverse square relationship and the proportionality to the product of the charges.
That's pretty impressive considering the technology he had available at the time.
It really is. And Coulomb's law has been verified to incredible precision over the years. It's one of the most fundamental laws of physics.
Okay, so we've got this formula now. How do we actually use it in practice?
Well, let's say you want to find the force between 2 charged particles.
Okay.
First, you need to know their charges and the distance between them.
Right.
Then you just plug those values into Coulomb's law and you get the force.
Simple as that.
Well, sort of. You also have to pay attention to the direction of the force.
Oh, right, because force is a vector.
Exactly. So the force will act along the line connecting the charges, and it will be either attractive or repulsive, depending on the signs of the charges.
So if the charges are the same sign, the force will be repulsive.
Right. They'll push each other away.
And if the charges are opposite signs, the force will be attractive.
Exactly. They'll pull each other together.
Okay, and our source actually gives a really interesting example of this. It compares the electrostatic force between an electron and a proton to the gravitational force between them.
Yeah, and the difference is absolutely staggering.
How so?
Well, the electrostatic force is about 10 to the 39 times stronger than the gravitational force.
10 to the 39, that's like a 1 with 39 zeros after it.
Exactly. It's a truly mind-boggling number.
So gravity is incredibly weak compared to the electrostatic force.
It is at least at the level of fundamental particles.
And that's why we can often neglect gravity when dealing with charged particles.
Right. The electrostatic forces are just so dominant.
Okay, so we've talked about the force between 2 charges. What happens if we have more than two charges?
Ah, that's where the principle of superposition comes in.
Superposition.
Yeah, it's a very powerful principle that allows us to handle multiple charges.
So what does it say?
Well, it basically says that the net force on any given charge is equal to the vector sum of the forces due to all the other charges individually.
Okay, so each charge acts as if the other charges weren't even there.
Exactly. Their influences just add up independently.
So if we have three charges, the force on one of them would be the vector sum of the forces from the other two.
Right. And if we have 100 charges, the force on one of them would be the vector sum of the forces from the other 99.
Okay, that could get pretty messy to calculate.
Yeah, but thankfully we have computers to help us with that these days.
Right. Technology to the rescue.
And our source provides a couple of examples of how to apply the principle of superposition to calculate the net force on a charge in different situations.
Okay, so it's good to see how the theory works out in practice.
It is, and it really highlights the power of this principle.
Okay, so we've got a good grasp of electrostatic forces. Now let's move on to the concept of the electric field.
Yeah, the electric field is a really important concept in electromagnetism.
So what is it exactly?
Well, instead of thinking about the force between two charges directly, we can think about a charge creating a field around itself.
A field
Like a region of influence that extends out into space.
Okay, and how does that help us?
Well, it allows us to separate the source of the electric force from the object experiencing the force.
So it's like saying instead of thinking about the sun directly pulling on the Earth,
Right.
we think about the sun creating a gravitational field and the Earth responding to that field.
Exactly. And it's the same idea with electric charges.
Okay, so how do we define the electric field?
Well, we define it as the force per unit charge that a small positive test charge would experience if it were placed at a particular point in space.
Okay, so it's like a measure of the electric force that a charge would feel at that location.
Exactly. And the direction of the electric field is the direction that a positive test charge would move if it were free to do so.
So if we place a positive test charge in an electric field, it will be pushed in the direction of the field.
Right. And if we place a negative test charge, it will be pushed in the opposite direction.
Okay, so the electric field tells us both the magnitude and direction of the electric force at any point in space.
Exactly. And we can visualize the electric field using electric field lines.
Field lines.
Yeah, they're imaginary lines that show the direction of the electric field at every point.
Okay, so how do we draw these field lines?
Well, we start by placing a positive test charge at some point in the field.
Okay.
Then we let the charge move freely and we trace out its path.
So the field line follows the trajectory of the test charge.
Exactly, and we can repeat this process for many different starting points to get a bunch of field lines.
Okay, and what do these field lines tell us?
Well, first of all, the direction of the electric field at any point is tangent to the field line passing through that point. Yeah, so if you draw a line that just touches the field line at a particular point, the direction of that line is the direction of the electric field.
Okay, and what else do the field lines tell us?
Well, the density of the field lines indicates the strength of the electric field.
Density.
Yeah, so where the field lines are closer together, the field is stronger.
And where they're farther apart, the field is weaker.
Exactly, and the field lines never cross each other.
Why not?
Well, if they did cross, it would mean that the electric field at that point would have two different directions.
Right.
And that's not physically possible. The electric field at any point must have a unique direction.
Okay, so the field lines are a nice visual way to represent the electric field.
They are, and they can be really helpful for understanding the behavior of charges in electric fields.
Our source provides some examples of electric field lines for different charge configurations.
Yeah, like for a single point charge, the field lines radiate outwards in all directions.
Okay.
And for two opposite charges, the field lines start at the positive charge and end at the negative charge.
So the field lines always go from positive to negative.
That's right. And the pattern of the field lines can get pretty complicated for more complex charge distributions.
But the basic principle is always the same.
Right. The field lines show the direction and strength of the electric field at every point in space.
Okay, now let's talk about electric flux.
Electric flux?
Yeah, it sounds kind of mysterious.
It's not really. It's just a measure of how much electric field passes through a given surface.
Okay, so it's like the flow of electric field through a surface.
Yeah, kind of. And it's important to note that there's no actual movement of charge in an electric field.
Right, it's just a measure of how much of the field is present at the surface.
Exactly. And to calculate the electric flux, we use the dot product of the electric field vector and the area vector of the surface.
Dot product.
Yeah. It's a way to multiply two vectors and get a scalar.
Okay, and the area vector is just a vector that's perpendicular to the surface and has a magnitude equal to the area.
Right, so if the electric field is perpendicular to the surface, the flux will be maximum. And if the electric field is parallel to the surface, the flux will be zero.
So the angle between the electric field and the surface matters.
It does, and we use the cosine of the angle in the dot product formula.
Okay, so if the angle is 0 degrees, meaning the electric field is perpendicular to the surface, the cosine is 1, and the flux is maximum.
Right, and if the angle is 90 degrees, meaning the electric field is parallel to the surface, the cosine is 0, and the flux is 0.
Okay, makes sense.
And to get the total flux through an entire surface, we just divide the surface into small area elements and sum up the flux through each element.
So it's like integrating over the surface.
Exactly, and the unit of electric flux is Newton meters squared per Coulomb.
Okay, so we've got electric flux. Now let's move on to something called an electric dipole.
An electric dipole?
Yeah, what is that?
Well, it's a system consisting of two equal and opposite charges separated by a small distance.
So it's like a positive charge and a negative charge right next to each other.
Exactly, and even though the total charge of the dipole is 0, it still creates an electric field. Well, the positive and negative charges create electric fields that point in opposite directions.
Right.
But because the charges are separated, the fields don't perfectly cancel out.
So there's a net electric field around the dipole.
Exactly. And this field has some interesting properties.
Properties like?
Well, first of all, the field strength falls off more rapidly with distance than the field of a single charge.
So it's a weaker field.
Yeah, at large distances, it falls off as 1 over r cubed instead of 1 over r squared.
Okay, and what else?
Well, the field also has a specific directionality.
Directionality.
Yeah, so along the axis of the dipole, meaning the line connecting the two charges,
Right.
the field points from the negative charge to the positive charge.
Okay.
And in the plane perpendicular to the axis, the field points from the positive charge to the negative charge.
So the direction of the field depends on where you are relative to the dipole.
Exactly. And to quantify the strength and orientation of the dipole, we introduce the concept of the electric dipole moment.
Dipole moment.
Yeah, it's a vector quantity that points from the negative charge to the positive charge and has a magnitude equal to the product of the charge and the separation distance.
Okay, so the dipole moment tells us everything we need to know about the dipole.
It does, and it's useful for describing the interaction of dipoles with electric fields.
Okay, so what happens if we place a dipole in an external electric field?
Well, the field will exert forces on the two charges of the dipole.
Right.
And these forces will generally create a torque on the dipole.
A torque.
Yeah, meaning a twisting force that tries to align the dipole with the field.
So it's like the field is trying to get the dipole to line up with it.
Exactly. And the magnitude of the torque is proportional to the dipole moment, the strength of the electric field, and the sign of the angle between them.
Okay, so if the dipole is already aligned with the field, the torque will be 0.
Right? Because the sign of 0 degrees is 0.
And if the dipole is perpendicular to the field, the torque will be maximum.
Exactly, because the sign of 90 degrees is 1.
Okay, and this torque is what causes polar molecules to align themselves with electric fields.
That's right. It's a very important phenomenon in materials science and chemistry.
Okay, so we've covered point charges and dipoles. Now let's move on to continuous charge distributions.
Continuous charge distributions.
What are those?
Well, they're basically systems where the charge is spread out over a region of space instead of being concentrated at discrete points.
Okay, so like a charged metal plate or a charged wire.
Exactly. And to describe these distributions, we use charge densities.
Charge densities.
Yeah, so for a linear charge distribution, like a wire, we use linear charge density, which is the charge per unit length.
Okay.
And for a surface charge distribution, like a plate, we use surface charge density, which is the charge per unit area.
Right.
And for a volume charge distribution, like a cloud, we use volume charge density, which is the charge per unit volume.
Okay, so it's just a way to quantify how much charge is packed into a given region of space.
Exactly. And to find the electric field due to a continuous charge distribution, we can still use the principle of superposition.
Superposition.
Yeah, we just divide the distribution into tiny charge elements and treat each element as a point charge.
Okay.
Then we calculate the electric field due to each element and add them all up vectorially.
So it's like integrating over the entire distribution.
Exactly. And that can get pretty tricky mathematically, but it's the basic idea.
Okay, now let's talk about Gauss's law.
Gauss's law.
Yeah, it's one of the fundamental laws of electromagnetism.
It is, and it provides a very elegant way to calculate electric fields in situations with symmetry.
Symmetry.
Yeah. So, for example, if we have a spherically symmetric charge distribution,
Okay.
then Gauss's law tells us that the electric field at any point outside the distribution is the same as if all the charge were concentrated at the center of the sphere.
Really? So we can treat the entire distribution as a point charge?
Exactly, as long as we're outside the distribution.
Okay. And what about inside the distribution?
Well, that depends on the specific distribution, but Gauss's law can still help us calculate the field.
Okay, so how does Gauss's law actually work?
Well, it relates the electric flux through a closed surface to the charge enclosed by that surface.
Electric flux.
Right, we talked about that earlier. It's a measure of how much electric field passes through a surface.
Right.
So Gauss's law says that the total electric flux through any closed surface is equal to the charge enclosed by the surface divided by the permittivity of free space.
Permittivity of free space.
Yeah, it's just a constant that we denote by epsilon naught.
Okay, and what's the significance of this law?
Well, it means that if we know the charge enclosed by a surface, we can easily calculate the electric flux through that surface.
And if we know the electric flux, we can sometimes use it to calculate the electric field.
Exactly, especially in cases with symmetry.
Okay, so Gauss's law is a powerful tool for calculating electric fields.
It is, and it's also very useful for understanding the concept of electric potential, which we'll talk about in a later episode.
Okay, so we've covered a lot of ground today. We've talked about charge, Coulomb's law, electric fields, electric flux, electric dipoles, continuous charge distributions, and Gauss's law.
Yeah, that's a pretty comprehensive overview of electrostatics.
And it's amazing to think that all of this complexity stems from the simple observation that rubbed amber attracts bits of fluff.
It really is. It's a testament to the power of scientific inquiry.
And as always, we encourage our listeners to delve deeper into this fascinating subject. There's always more to learn.
Absolutely. And we'll be back next time with another deep dive into the world of physics.
Until then, stay curious.
And keep exploring.
All right, that's it for this episode, folks.
Thanks for listening.
We'll see you next time.
Bye for now.
Chapter 2. Electrostatic Potential and Capacitance.
Hey everyone, welcome back to the Deep Dive. We are all about taking dense, complex topics and figuring out the need-to-know info. And today we're diving into a world that's, well, kind of invisible. We're talking all about electrostatic potential energy, like how much energy is packed in the space around an electric charge.
Yeah, it's kind of like mapping out this hidden energy landscape, right?
Yeah,
We're
sure.
going to be building off of some stuff you probably learned in earlier physics classes. I'm talking like chapter 5 and 7 stuff from class 6i, like gravitational potential energy and spring potential energy. Remember all that?
Totally. So we learned about how when you work against a force, like when you lift something up against gravity,
Right.
or when you stretch a spring, that work doesn't just disappear, it gets stored, becomes potential energy.
Exactly. It's stored just waiting to be released.
Yeah.
And what's really neat is that the Coulomb force, the force between electric charges, plays by the same rules. It's a conservative force, too.
Oh, I see. So we're making a connection here between forces that seem like totally different. Gravity, springs, and now electric charges.
Exactly. And it's a really powerful connection because it lets us use a lot of the same ideas and concepts. I mean, think about it. Gravity has that inverse square law. The force gets weaker with distance.
Right.
Well, guess what? Coulomb's law for electric charges. Same deal. Inverse square law. One's got masses, the other's got charges. But the underlying math, the structure, it's super similar.
Okay, so how does this actually work with, electric fields?
All right, so picture this. You've got a charge, Q, just hanging out, creating an electric field around itself. Now let's bring in another charge, a tiny test charge. We'll call it Q. We're going to move this little Q from one point R to another point P, and we're going to do it very, very carefully so it doesn't speed up or slow down, no acceleration.
Okay, I'm picturing it. So what happens?
Well, if Q and Q are both positive or both negative, they're going to repel each other, right? So to move little q closer, we're going to have to push against that repulsive force. We're going to have to do some work.
Ah, okay, so that's where the energy comes in, the effort we put in.
Right. And that work we do, it gets stored. It becomes potential energy. And specifically the amount of work we do, it's exactly equal to the difference in potential energy between those 2 points, P and R.
Gotcha. So if it takes, say, 10 units of work to move Q from R to P, then the potential energy at P is 10 units higher than at R.
Precisely. Now, here's a really cool thing about this, and it's all because the electrostatic force is conservative. It's just like with gravity. If you take a book from a table and lift it up to a shelf, it doesn't matter if you lift it straight up or if you take some crazy loopy path. The work you do only depends on the difference in height, the starting point, and the ending point.
Oh, that's interesting. So it's the same with moving charges in an electric field. The path you take doesn't matter.
Exactly. Only the starting and ending points matter.
Wow.
And that's super important because, well, if the work depended on the path, then the idea of a single well-defined potential energy, it wouldn't really make sense, right?
Right. That makes sense.
Now, we could go through all the math to prove this using Coulomb's law, but I think we can trust that the physicists got it right this time. The takeaway is that it's the difference in potential energy that really matters.
Okay, so if the difference is what matters, that means we can kind of choose where we want to set the 0 point for potential energy, right? Kind of like we choose where to put the 0 on a ruler.
Exactly. And the most convenient choice, the one that makes the math the easiest, is to put that 0 point way out at infinity. Think about it. If our starting point R is infinitely far away from all the charges, then there's no electric field, no force to worry about.
Right, so the potential energy at infinity is just 0.
Right. So then the potential energy at any other point P, it's just the work done to bring a charge from infinity to that point. Nice and simple.
That's pretty clever. Now, I've heard about something called electrostatic potential. Is that related to this potential energy stuff?
It is, but instead of talking about the potential energy of a specific charge, we zoom out and think about the work done per unit of charge. So it becomes more like a property of the space itself, independent of whatever charge we're using to test it.
Oh, okay, so it's like a more general way to describe the electrical landscape?
Precisely. So if we take a unit positive charge and move it from point R to point P, the work done is exactly equal to the potential difference between those 2 points, which we write as Vp minus Vr.
And again, it's that difference that matters, right?
Absolutely. And just like with potential energy, we set the 0 point for potential at infinity. So the potential at any point is just the work needed to bring a unit positive charge from infinity to that point.
Makes sense. But wait, if we're talking about a unit charge, won't that charge itself mess up the electric field?
That's a great point. To be technically correct, we actually think about using an infinitesimally small test charge, like dq, to avoid disturbing the original charges. But for simplicity, we often just talk about a unit charge.
Okay, I got it. So now for a more concrete example. What's the potential created by a single point charge?
All right, so let's say we've got a point charge q hanging out at the origin of our coordinate system, and we want to find the potential at a point that's a distance there away. Well, the formula turns out to be pretty simple. It's q divided by 4 pi epsilon naught times r. Epsilon naught is just a constant that tells us how easily electric fields can pass through empty space.
Okay, I'm following. So if Q is positive, then the potential at that point is positive too.
Right. And that makes sense, right? Because if you try to bring another positive charge closer to Q, you're going to have to push against that repulsive force. You have to do work. So the potential, which is like the work per unit charge, is positive.
Right, like climbing an electric hill.
Exactly. Now, what if Q is negative? Well, then the potential is negative, meaning that you'd actually gain energy by bringing a positive charge closer. It's like rolling down an electric hill.
So the formula works for both positive and negative charges. Neat.
Yeah, it's pretty elegant. And, the source material actually has this really cool figure 2.4, that shows how the potential changes with distance compared to the electric field.
Oh, cool. Let me see. Yeah, I see it. So the potential falls off more gradually than the electric field, right?
Exactly. The potential goes like 1 over r, while the electric field goes like 1 over r squared.
So the electric field gets weak much faster as you move away.
Yeah.
Makes sense.
Yep. Let's try a quick calculation. Example 2.1 says we have a 4 times 10 to the negative 7 coulombs charge. What's the potential 9 centimeters away?
Okay, let me grab my calculator. All right, so plugging in the numbers, I get 4 times 10 to the 4th volts.
Spot on. Now, what if we wanted to bring a 2 times 10 to the negative 9 coulombs charge from infinity to that point? How much work would that take?
Well, work is just charge times potential, right? So
It would be.
8 times 10 to the negative 5 joules.
Exactly. And remember, because the electrostatic force is conservative, the path we take to bring that charge in doesn't matter. We could take a straight line, a spiral, whatever. The work is the same.
All right, that's really starting to sink in now. But can we make things a little more complicated?
Sure, let's talk about electric dipoles.
Oh, yeah, those. I remember something about those from my physics classes. They were always kind of tricky.
Yeah, they can be a bit more involved, but they're super important. So a dipole is basically just two equal but opposite charges separated by a small distance. We usually call that distance 2a. And this separation gives the dipole something called a dipole moment, which is a vector. It points from the negative charge to the positive charge, and its magnitude is 2a.
Okay, so we're talking about like a plus q and a minus q charge, a little distance apart.
Exactly. Now, the cool thing about dipoles is how their electric field behaves far away. Remember how the field of a single charge falls off like 1 over r squared?
Yep.
Well, the field of the dipole, it falls off much faster, like 1 over r cubed. That's because, from far away, those positive and negative charges start to cancel each other out.
Ah, that makes sense. So what about the potential due to a dipole?
Well, since potential obeys the superposition principle, which means the total potential is just the sum of the potentials from each charge, we can just add up the potentials from the plus q and the minus q. And after some math, especially when r is much bigger than a, we get this nice approximate formula for the potential.
What's the formula?
It's p cos theta, all divided by 4 pi epsilon naught r squared. Theta is the angle between the line connecting the dipole to r point and the dipole moment vector.
Okay. And is there like a special significance to that p cos theta part?
Yeah, actually, it's the dot product of the dipole moment vector and a unit vector pointing from the dipole to our point. So we could write it as p dot r hat all over 4 pi epsilon naught r squared. And this formula, it becomes exact if we imagine a point dipole, which is basically a dipole where the separation between the charges is super tiny, but the dipole moment stays the same.
Okay, so it's like a theoretical ideal dipole.
Exactly. And it's super useful for making calculations simpler. So what does the potential look like for different angles, theta? Well, if theta is 0 or 180 degrees, which is like being along the axis of the dipole, the potential is non-zero. But if theta is 90 degrees, which is like being in the plane that cuts the dipole in half, the potential is 0.
Ah, that's because in that plane, you're basically the same distance from the positive and negative charges, so their potentials cancel out, right?
Exactly. So we see two big differences between the potential of a dipole and the potential of a single charge. First, the dipole potential depends on the angle, not just the distance. And second, it falls off faster as 1 over r squared compared to 1 over r for a single charge. That tells you the dipole is overall neutral, from far away.
Okay, that's really helpful. So what about more complicated scenarios? What if we have like a whole bunch of charges?
Well, thankfully, the principle of superposition still holds. It means that the total potential at a point due to a bunch of charges is just the sum of the potentials due to each individual charge. Easy peasy.
So just calculate the potential from each charge and add them all up.
Exactly, and that's often a lot simpler than dealing with electric fields, which are vectors and require vector addition.
Right, that makes sense. But what about cases where the charge isn't all concentrated in points? Like, what if we have a charged rod or a charged disk?
In those cases, we bring in the power of calculus. We imagine the continuous charge distribution as being made up of infinitely many tiny point charges, dq, and then integrate over the whole thing.
Integration, my favorite. Seriously, that's pretty cool.
Right. It's amazing how calculus can handle these continuous distributions. For example, take a uniformly charged spherical shell. Outside the shell, the potential is exactly the same as if all the charge were concentrated at the center of the sphere. It's like magic.
Wow, that's pretty neat. But what happens inside the shell?
Inside. Well, remember Gauss's law. It tells us that the electric field inside a uniformly charged spherical shell is 0. And since the electric field is the negative gradient of the potential, that means the potential inside must be constant.
So the potential is the same everywhere inside the shell.
Exactly. And it's equal to the potential at the surface of the shell.
Interesting, like a flat electric landscape inside the shell.
Perfect analogy. Now, how about we try another example? Example 2.2 throws us a curveball. We've got 2-point charges, a 3 times 10 to the negative 8 coulombs, and a negative 2 times 10 to the negative 8 coulombs, separated by 15 centimeters. The question is, where is the potential 0?
Okay, so we need to find the points where the potentials from the positive and negative charges cancel out.
Exactly. And after a bit of algebra, we find that there are actually 2 points where the potential is 0. One is 9 centimeters away from the positive charge, and the other is 45 centimeters away from the positive charge.
So even with just 2 charges, the potential landscape can be pretty complex.
Yep. And example 2.3 dives even deeper, looking at the signs of potential differences, changes in potential energy, and the work done by the electric field. It really gets you thinking about how everything connects.
Like all the different aspects of potential and energy.
Exactly. Now, are you ready to add another tool to your electrostatic toolbox?
Always up for new tools. What is it?
It's called an equipotential surface. It's a surface where the electric potential has the same value at every point. Think of it like a contour line on a topographic map, but instead of showing elevation, it shows electric potential.
Oh, that's cool. So it's like a visual representation of the potential landscape.
Exactly. And for a single point charge, what do you think the equipotential surfaces look like?
Well, since the potential only depends on the distance from the charge, I guess the equipotential surfaces would be spheres, right? Like concentric spheres centered on the charge.
You got it.
Yeah.
Now here's a really important relationship. The electric field at any point is always perpendicular to the equipotential surface passing through that point.
Why is that?
Well, imagine moving a test charge along an equipotential surface. Since the potential is constant, no work is done. If the electric field had a component along the surface, then moving a charge along that component would mean work is being done, right?
Right.
So the electric field can only have a component perpendicular to the surface.
Oh, that makes sense. So the electric field lines are like piercing those equipotential surfaces at right angles.
Exactly. So equipotential surfaces give us a different way to visualize electric fields. We can picture these surfaces, and then the field lines are always perpendicular to them, pointing in the direction of decreasing potential.
I like that. It's like instead of drawing arrows for the field lines, we're drawing these contour maps of potential.
Right. And the source material has some great examples of this. Figure 2.10 shows equipotential surfaces for a uniform electric field. They're just planes perpendicular to the field lines. And figure 2.11 shows more complex shapes for a dipole and a system of two positive charges.
Cool. Yeah, I see how the field lines always intersect the surfaces at right angles.
Right. And there's a neat mathematical relationship, too. If we take two really close equipotential surfaces with potentials V and V plus dV, and the distance between them is dLL, then the electric field is just the negative derivative of the potential with respect to distance.
So E equals negative dV by dL.
You got it. And that negative sign is important. It tells us that the electric field points in the direction of decreasing potential, like how a ball rolls downhill.
Right, always seeking the lowest potential energy.
Exactly. Now let's switch gears a bit and talk about the potential energy of a system of charges. Basically, it's the work needed to assemble those charges, bringing them together from infinity.
Okay, so we're not talking about a single charge in an external field anymore. We're talking about like multiple charges creating their own field.
Precisely. So let's start simple. Two charges, Q1 and Q2, separated by a distance R12. What's the potential energy of this system?
Well, I remember from physics class that it's proportional to the product of the charges and inversely proportional to the distance between them.
You're spot on. The formula is Q1 times Q2, all divided by 4 pi epsilon naught R12. Now, pay attention to the sign here. If both charges are positive or both are negative, their product is positive, which means the potential energy is positive. That makes sense because you had to do work to bring those charges together, pushing against their repulsion.
Right. It's like trying to push two magnets together with the same poles facing each other. You have to put in effort.
Exactly. But if the charges have opposite signs, then their product is negative, and so is the potential energy. That means energy is released when they come together because they attract each other.
Like opposite poles of magnets snapping together.
Perfect analogy. And this all extends to more than two charges. If you have three charges, you just add up the potential energy of each pair.
So like Q1 and Q2, Q1 and Q3, and Q2 and Q3.
Exactly. And it doesn't matter what order you bring the charges in, the final potential energy is always the same.
That's because the electrostatic force is conservative, right? The path doesn't matter.
You got it. Example 2.4 actually demonstrates this. It walks us through calculating the work needed to assemble 4 charges at the corners of a square. It's a cool way to see how this potential energy stuff works in practice.
Right, because the work you do is equal to the change in potential energy.
Precisely. The example even asks about the work needed to bring a 5th charge to the center of the square.
Interesting. What happens in that case?
Well, it turns out that in this symmetrical configuration, the potential at the center due to the 4 corner charges is 0. So no additional work is required to bring in the 5th charge.
Wow, that's pretty cool. So the potential can be 0 even in a region with charges around.
Exactly. It all depends on the arrangement of the charges. Now, we've been talking about systems where the charges are the source of the field, right? But what if we put a single charge into an electric field that's created by some other charges?
Ah, good point. So now we're back to talking about an external field.
Right. So let's say we have a single charge Q sitting in an external field with potential V of R. What's its potential energy?
Well, if I had to guess, I'd say it's just the charge times the potential.
You nailed it. It's just Q times V of R. Simple as that. But it's crucial to remember that V of R is the potential created by those other charges, not the charge Q itself.
Right, that makes sense.
And this brings us to a handy unit of energy that's often used in atomic and nuclear physics, the electron volt, or EV. 1 electron volt is just the energy gained by an electron when it moves through a potential difference of 1 volt.
Oh yeah, I've heard of that unit. It's much smaller than a joule, right?
Right. It's about 1.6 times 10 to the negative 19 joules. It's a lot more convenient when dealing with tiny particles.
Makes sense. So we can use electron volts to talk about the energy of, like, electrons orbiting an atom.
Exactly. Now, what if we have two charges, Q1 and Q2, sitting in an external field? Well, their total potential energy is the sum of their individual potential energies due to the field, plus the potential energy due to their interaction with each other.
Okay, so it's a combination of the external field and their own internal interaction.
Exactly. And example 2.5 walks us through a calculation just like this, showing how to find the total potential energy of two charges in a uniform external field.
Cool. So we're building up our problem-solving skills here.
We are. Now, for our final act, let's consider an electric dipole in a uniform external electric field. Remember how a dipole experiences a torque in an electric field that tries to align it with the field?
Yep, I remember.
Well, if we want to rotate the dipole against that torque, we have to do work, and that work gets stored as potential energy.
So the potential energy depends on the angle between the dipole and the field.
Exactly. The formula is negative P dot E, where P is the dipole moment and E is the electric field. We often choose the potential energy to be 0 when the dipole is perpendicular to the field.
Okay, that makes sense. So the dipole has the lowest potential energy when it's aligned with the field.
Right, and you know what? This formula is actually consistent with the formula for the potential energy of two charges in an external field. It all comes together beautifully.
Nice. I love it when different parts of physics connect like that.
It's one of the best parts of physics. Now, example 2.6 gives us a really interesting real-world application of this. It looks at a mole of polarized molecules and how much heat they release when the direction of the electric field changes. That heat comes from the change in the potential energy of those little dipoles as they reorient themselves with a new field.
Wow, that's pretty wild. So we're talking about, like, molecular level energy changes here.
We are. Now, are you ready to dive into the world of conductors?
Always. Let's do it.
All right. So conductors are materials that have tons of free charges, like electrons that can move around easily. And when a conductor is in electrostatic equilibrium, meaning no charges are flowing, it has some really cool properties. First off, the electric field inside a conductor is always 0.
Why is that?
Well, if there was an electric field inside, those free charges would feel a force and start moving. And that wouldn't be equilibrium anymore, right?
Right. The charges would keep moving until the field is 0.
Exactly. Now, what about the electric field at the surface of a conductor? It turns out that it has to be perpendicular to the surface.
Why is that?
Well, if there was a component of the field parallel to the surface, the free charges on the surface would feel a force and redistribute themselves until that parallel component is gone.
Ah, so they move around until they're in a configuration where the field is perpendicular.
Right. It's like they're smoothing out any bumps in the electric field at the surface. Another cool thing about conductors is that any excess charge you put on them always ends up on the outer surface. None of it stays inside. That's a direct consequence of Gauss's law.
Okay, I remember Gauss's law. It relates the electric field to the enclosed charge.
Exactly. And since the field inside is 0, there can't be any net charge enclosed inside a Gaussian surface that's entirely within the conductor.
So all the excess charge is pushed out to the surface.
Yep. Now, what about the potential inside a conductor?
Well, since the electric field is 0 inside, I'm going to guess that the potential is constant throughout the conductor.
You are a potential guessing pro. That's exactly right. And since the potential is constant, that means there's no potential difference between any 2 points inside the conductor or between any 2 points on the surface.
Right, because the potential difference is just the work done per unit charge, and no work is done if you move a charge through a 0 electric field.
Perfect. Now, we can actually calculate the electric field just outside the surface of a conductor. It turns out to be proportional to the surface charge density, which is just the charge per unit area.
So it's the formula.
It's E equals sigma divided by epsilon naught, where sigma is the surface charge density, and the field points outward, perpendicular to the surface.
Okay, so the more charge you pack onto the surface, the stronger the field just outside.
Exactly. And this all leads to a really important concept, electrostatic shielding. If you have a conductor with a hollow cavity inside, the electric field inside that cavity is zero, no matter what's going on outside.
Wait, really? So you could be like in a lightning storm, but if you're inside a hollow metal sphere, you'd be perfectly safe.
Well, in theory, yes. As long as the metal sphere is a good conductor and there are no charges inside the cavity, you'd be totally shielded from the external electric fields. That's why a Faraday cage works.
That's incredible. So it's like the conductor creates a safe haven from electric fields.
It does. And the shielding effect is super important in all sorts of applications, from protecting sensitive electronic equipment to designing safe storage for flammable materials. Figure 2.19 in our source gives a great visual overview of all these conductor properties.
Yeah, that figure is really helpful. Now, example 2.7 connects these conductor properties to a bunch of real-world phenomena. It explains why a charged comb can attract pieces of paper, why aircraft tires are sometimes made conductive, and why birds can chill on power lines without getting zapped. It's super cool to see how these abstract concepts actually play out in everyday life.
I know, right? It's like physics is all around us. Now, speaking of materials, let's talk about dielectrics, which are basically insulators. These are materials that don't have many free charges to move around.
Okay, so they're the opposite of conductors.
Right, and when you put a dielectric in an electric field, something interesting happens. Instead of free charges moving, the molecules inside the dielectric get polarized.
What does polarized mean?
It means that the molecules develop little electric dipoles, kind of like the dipoles we talked about earlier. This can happen in two ways. For nonpolar molecules, which don't have a permanent dipole moment, the electric field stretches or distorts the electron cloud, creating a temporary dipole. For polar molecules, which already have a permanent dipole moment, the electric field just aligns those dipoles.
Oh, I see. So the electric field is kind of like influencing those little molecular dipoles.
It is. And all those tiny dipoles add up, creating an electric field that opposes the external field. But it doesn't completely cancel it out like in a conductor.
Right, so the field inside the dielectric is weaker than the external field.
Exactly. Now, in linear isotropic dielectrics, the induced dipole moment is proportional to the electric field. We define this thing called the polarization P, which is just the dipole moment per unit volume.
Okay, so it's a measure of how polarized the material is.
Right. And for linear dielectrics, the polarization is proportional to the electric field. We write it as P equals epsilon naught times chi times E naught, where chi is the electric susceptibility. It tells you how easily the material gets polarized.
Okay, got it. So is there a connection between this polarization and the electric field inside the dielectric?
There is. It turns out that a uniformly polarized dielectric behaves like it has surface charge densities on its surfaces. These are called bound charges, and they create an electric field that opposes the external field, making the field inside weaker.
Interesting. So the dielectric kind of like fights back against the external field.
Yeah, you could say that.
Yeah.
Now, this whole concept of dielectrics brings us to capacitors.
Capacitors, those are those things that store electric charge, right?
Got it. A capacitor is basically two conductors separated by an insulator, which can be a vacuum or a dielectric. And when you put charges on the conductors, a potential difference builds up between them.
And the amount of charge you can store depends on the capacitance.
Exactly. The relationship is Q equals CV, where Q is the charge, V is the potential difference, and C is the capacitance. And the capacitance depends only on the geometry of the capacitor and the material between the conductors.
So a bigger capacitor, or one with a different dielectric material, can store more charge at the same voltage.
Precisely. And the unit of capacitance is the farad, but a farad is actually a huge amount of capacitance. In practice, we usually use microfarads, nanofarads, or even picofarads.
Right. I've seen those units on capacitors before.
Yep. Capacitors are super important in circuits, especially in AC circuits, which we'll talk about later. But for now, let's focus on a simple capacitor, the parallel plate capacitor. It's just two big flat plates separated by a small distance.
Okay, I can picture that.
Now, if there's a vacuum between the plates and we put charges plus Q and minus Q in them, we get a uniform electric field between the plates. And we can ignore the field outside the plates because of edge effects.
Right, we're assuming an ideal capacitor here.
Exactly. So the potential difference between the plates is just the electric field times the distance between the plates. And from that, we can get the capacitance. C naught equals epsilon naught times A over D, where A is the area of the plates and D is the separation.
So the capacitance depends on the size of the plates and how far apart they are.
Exactly. And the bigger the plates or the smaller the distance, the higher the capacitance. But even with big plates and a small distance, the capacitance is still pretty small.
Yeah, a farad is a big unit.
It is. To get a 1 farad capacitor with plates 1 centimeter apart, you'd need plates that are like 30 kilometers by 30 kilometers.
Wow, that's enormous. Okay, so what happens when you put a dielectric between the plates?
Well, remember how the dielectric gets polarized? That polarization creates bound charges on the surfaces of the dielectric, which reduces the electric field between the plates.
So the potential difference decreases for the same amount of charge.
Exactly, and that means the capacitance increases. It turns out that the capacitance with the dielectric is just K times the capacitance without the dielectric, where K is the dielectric constant.
Ah, so the dielectric constant tells you how much the capacitance increases.
Right, and we can define the permittivity of the dielectric as epsilon equals K times epsilon naught. So the dielectric constant is just the ratio of the permittivity of the dielectric to the permittivity of free space.
Okay, that.
Chapter 3. Current Electricity.
Okay, so electric current, you know, it's everywhere.
It really is.
Powering our lives. You
Yeah.
hear about it all the time. Whether it's, you know, that little bit of current that's making your smart speaker work, or, you know, a huge bolt of lightning that, you know, makes the lights flicker.
Yeah, the range is incredible.
Incredible. It's the same fundamental phenomenon, just, you know, different delivery mechanisms and scales.
Absolutely.
And for this deep dive, you've sent in a bunch of really cool material, and we're going to try to, you know, go through it and figure out what electric current is all about.
Yeah, let's really unpack this because it's something that we sort of take for granted, I think, in a lot of ways.
Me too.
But, you know, it's responsible for so much of our modern lives.
Right.
So starting with the basics, what is electric current?
Well, it's a movement of charge.
Okay,
And, you know, we can think about it kind of like water flowing through a pipe.
right.
But instead of water molecules, we're talking about electric charge. And the way that we quantify it, you know, there's a very basic definition, and you'll see this as I equals Q over T.
Right.
It's the net amount of charge. And that's really important.
Yeah.
It's not just, you know, charges moving around.
Right.
It's the net amount of charge that's passing through a given area in a given amount of time. So, you know, it's like how much charge is actually making it through a certain point.
And so we've got to be careful about that net term, right?
Yes.
Because it's the positive charge moving in one direction minus the negative charge moving in the other direction.
Right.
It's that overall sort of one-way flow.
Right. It's the overall sort of drift.
Yeah.
You can think of it kind of like, you know, trying to get into a concert and there's a big crowd of people
Right.
and, you know, some people are coming in, some people are going out, but the net flow is, you know, how many people are actually making it through that gate.
Yeah, that's a great analogy.
And that's basically what current is.
Okay, so we've got this nice picture now for a steady current. You know, something like you'd get from a battery powering a device.
Right.
But what about when things are not so smooth?
Exactly.
When it's not just a nice even flow?
Right. So sometimes we don't have a steady current.
Yeah.
We have an unsteady current.
Yeah.
You know, sometimes it's not just that, you know, gentle stream from the tap. It's, you know, a sudden downpour.
Okay.
So how do we quantify that?
Yeah. How do we define that mathematically?
Well, instead of looking at, you know, a large chunk of time,
Right.
we're going to take a very small slice of time,
Right.
you know, an infinitesimally small slice of time,
Okay.
and see how much charge passes through during that instant. And we call that delta cat.
Right.
The very small slice of time in delta Q is the small bit of charge that flows.
Yeah.
And so the instantaneous current, which we can call I of tat, is what happens when that delta cat, you know, gets closer and closer to zero.
Right. So we're taking the limit
Yes.
as that time interval gets very, very tiny.
Exactly.
Okay. So we've got a way to handle steady currents and unsteady currents now.
Yeah.
How do we actually measure this thing?
We'll use a unit called the ampere, or amp for short, or you'll see it as a capital A.
Right. And the ampere, that's our SI unit for measuring current.
Right.
And it's incredible to think about the range of scales that this unit covers.
It is.
Right? I mean, your typical household appliance might draw, you know, a few amps.
Right.
But then you look at something like a bolt of lightning, and you're talking tens of thousands of amps.
Right. It can really ruin your day.
Yeah, exactly. And on the other end of the spectrum, The signals in our nervous system,
Right.
those tiny electrical impulses,
Hmm.
those are on the order of microamps.
Right. A millionth of an amp.
A millionth of an amp. Incredible.
Incredible.
So from, something that could vaporize a tree
Right.
to the tiny signals in our bodies,
Right.
it's all about the flow of charge, this electric current.
It is. So we've got these charges moving. What's motivating them to move in the first place?
Right. What's the driving force behind all of this?
Yeah.
Well, it comes down to electric fields. And you might remember from a previous deep dive when we talked about electrostatics.
Right.
Electrostatics is all about stationary charges and the fields that they create.
Right.
Now, when we have charges that are free to move,
Mm-hmm.
that electric field exerts a force on them, and that force causes them to accelerate. And that movement of charge, that's what we define as electric current.
So if you've got an electric field, you've got the potential for current.
Right.
It's like having, a bowling ball at the top of a hill that's just waiting to roll down.
Exactly.
But not all materials are created equal, are they?
No, they're not.
When it comes to, allowing this flow of charge.
Right. Some materials are much more resistant to that flow
Right.
than others, and that brings us to a very important distinction between insulators and conductors.
Okay.
So in an insulator, a material like glass or rubber, the electrons are very tightly bound to the atoms.
Uh-huh.
And even if you apply an electric field, those electrons aren't really free to move around. They're stuck. They can't really contribute to a current. It's like trying to convince a bunch of, people sitting on their pouches to suddenly get up and run a marathon.
They're not going to do it.
They're not going to do it. They're just too comfortable. They're
Yeah.
too tightly bound to their comfy spots.
Exactly.
So those are insulators. Now, on the other hand, you have conductors, especially metals.
Right.
In a conductor, some of the electrons are essentially free to wander around.
Uh-huh.
Throughout the entire material, it's like they're at a big music festival.
Yep.
They can move around pretty easily within the venue.
Yeah, so the electrons are ready to party.
They're ready to party. They're ready to move.
Okay.
And so in a solid conductor, and this is what we'll be focusing on mostly,
Okay.
the current is carried by these negatively charged electrons moving through this sort of background lattice of positively charged ions.
Right.
So you can picture it almost like a game of Plinko,
Okay.
where you have these electrons, the little balls bouncing around,
Mm.
and those ions are the pegs, the stationary things that they're colliding with.
Right.
Now, even without an external electric field applied, those free electrons aren't just sitting still.
Right, they're always moving.
They're always moving. They have thermal energy.
Right.
And that thermal energy causes them to move around randomly.
Right, so it's like a mosh pit, but at the atomic level.
Exactly, a microscopic mosh pit.
Right.
So they're bumping into those ions, constantly changing direction.
Yeah.
And on average, each electron comes out of a collision with roughly the same speed it had before,
Mm-hmm.
but the direction is random.
Right.
So you've got electrons going every which way,
Yeah.
and if you average it all out, it cancels out.
Right.
There's no net flow.
No net flow.
There's no current.
Right, so no field, no net motion, no current.
Exactly.
Now what happens when we do introduce an electric field?
Well, that's when things get interesting.
Okay.
So now you've applied this electric field,
Uh-huh.
and those free electrons, they experience a force. And because they're negatively charged, they accelerate in the opposite direction to the field.
Okay.
They're attracted to the positive side.
Uh-huh.
So that acceleration, that causes a temporary current.
Right.
But it's temporary because eventually, if we just had like two charged plates creating that field,
Right.
those electrons would just pile up on the positive side,
Right.
and then the field would disappear.
Right, so it wouldn't be continuous.
Exactly.
So how do we get a continuous current?
Well, we need a way to maintain that electric field.
Okay.
And that's where devices like cells and batteries come in.
Okay.
They act like little charge pumps.
Okay.
They're constantly working to replenish the charges at the ends of the conductor.
Uh-huh.
So they're ensuring that there's always an electric field present.
Right, so like the road crew constantly clearing the path.
Exactly.
For our electrons to, slowly march along.
Exactly. A steady flow of traffic.
Right now, this flow isn't totally unimpeded, is it?
No, it's not.
There's this thing called resistance that gets in the way.
Exactly. Resistance. It's like friction in our water pipe analogy.
Yeah.
Or maybe like speed bumps on our electron highway.
Right.
It's that opposition to the flow of current. And there's a very fundamental law that describes this relationship.
Mm-hmm.
And it was actually discovered back in 1828 by a German physicist named Georg Simon Ohm.
Okay.
And this was even before scientists really understood what was going on with the electrons at the microscopic level.
Wow.
So Ohm's law, in its simplest form, states that the voltage V across a conductor is directly proportional to the current I flowing through it.
Okay.
And we write that as V equals IR,
Right.
where R is the resistance.
So higher resistance means you need a bigger push
Right, a larger voltage.
to get the same amount of current.
Exactly. Or if you have a fixed voltage, you'll get a smaller current if the resistance is higher.
Right.
It's like trying to push water through a really thin clogged pipe
Yeah.
versus a nice wide open pipe.
Right.
And the unit we use to measure resistance is the ohm, symbolized by the Greek letter omega.
Omega.
Now, this resistance, it's not just a property of the material itself.
Uh-huh.
It also depends on the shape and the size of the conductor.
Right, like the dimensions.
Exactly, the dimensions. So let's think about like a simple block of material.
Okay.
If you take two identical blocks and you connect them end to end, you've essentially doubled the length that the current has to travel through.
Right.
So what do you think happens to the resistance?
Well, if we think about our pipe analogy again,
Yeah.
Making the pipe longer means more friction.
Right. More surface area for the water to rub against.
Exactly. So I would guess that the resistance doubles.
You are exactly right. The resistance is directly proportional to the length.
Okay.
Now, what if instead of connecting them end to end, we put those two blocks side by side?
Okay, so the length is the same.
The length is the same, but now we've doubled the cross-sectional area.
Right. So we've made it wider.
Exactly. We've widened the pipe.
So what happens then?
What do you think happens to the resistance?
Well, if we're making the pipe wider,
Mm-hmm.
there's more room for the water to flow.
Right.
So it should be easier for the current to get through.
Absolutely.
So I would guess that the resistance goes down.
Yes. And in fact, if you double the area, you cut the resistance in half.
Okay.
So resistance is inversely proportional to the cross-sectional area.
Right.
So we've got these two relationships,
Mhm.
proportionality to length and inverse proportionality to area. And if you combine those, you find that the resistance R is equal to rho times L over A.
Okay.
Where rho, that's a property of the material itself, and we call that resistivity.
Okay.
So that's like the inherent stubbornness of the material to letting charge flow,
Right.
regardless of its shape or size.
So copper has a very low resistivity.
Very low.
It's a good conductor.
Exactly.
Whereas rubber has a really high resistivity.
Extremely high.
It's a good insulator.
Absolutely.
Now, we also came across this concept of current density,
Yes.
J.
J.
It sounds kind of intense. What is that?
Well, current density, it's essentially how concentrated the current is
Okay.
in a given area.
Uh-huh.
So it's defined as the total current I divided by the cross-sectional area A.
Right.
So J equals I over A.
Okay.
And the units for that are amps per square meter.
Right.
And just like current density is a vector quantity,
Okay.
meaning it has both magnitude and direction,
Right.
and it points in the direction of current flow.
So it's kind of like, how many electrons are trying to squeeze through a certain doorway?
Exactly, a great analogy.
So a thin wire is going to have a higher current density
Right.
than a thick wire for the same current.
Exactly, because you're forcing those electrons through a smaller space.
Right.
And you might recall that we talked about Ohm's law,
Yeah, V equals IR.
where E equals IR,
Yeah.
right? But we can actually express it in a slightly different way
Yeah.
using these intrinsic material properties.
Uh-huh.
So we can relate the electric field E to the current density J.
Okay.
So if you have a uniform electric field E across a conductor of length L,
Uh-huh.
the potential difference V across it is simply E times L.
Okay.
So if we substitute that into Ohm's law
Right.
and use our expressions for resistance and current density, we can rearrange things and we get E equals J times rho.
Okay, so instead of looking at, the overall voltage and current,
Right.
we're looking at the local electric field
Yeah, within the material.
and the current density that it
Uh-huh.
creates.
Exactly.
And just like we have resistivity,
Right.
we also have conductivity, which is the inverse.
Yes, the inverse of resistivity.
So it's like how easily the material allows current to flow.
Exactly. It's a measure of how good a conductor it is.
So a material with high conductivity is like a superhighway for electrons.
Exactly.
Now, it's fascinating to think that George Simon Ohm himself,
Yeah.
back in the early 19th century, he drew an analogy between electrical conduction
Oh, yeah.
and heat conduction.
Right.
So he was thinking, the electric field is kind of like a temperature gradient
Yeah.
that drives heat flow, and the electric current is analogous to the heat flow itself.
It's not a perfect analogy,
Right.
but it gave him a framework for understanding these relationships.
Wow. So even before, we really had a picture of electrons and all that,
Yeah.
there were these clues in other areas of physics
Right.
that suggested how current might behave.
Exactly.
Now, let's dive a bit deeper into what's happening with those electrons
Okay.
that's causing this resistance and this drift.
Right. So remember we said that without an electric field, the free electrons in a conductor, they're just bouncing around randomly.
Right, just due to that thermal motion.
Exactly, thermal motion.
So then we apply an electric field,
Uh-huh.
and each electron experiences a force,
Right.
and it starts to accelerate
Yeah.
in the direction opposite to the field.
Right, because it's negatively charged.
Right.
It's attracted to the positive side.
Okay.
But as they move, they're going to collide with those stationary positive ions.
Right, they can't just go unimpeded.
No, they can't. It's not a smooth ride. So they bump into those ions, and every time they collide, they lose that directed momentum
Okay.
that they gained from the field, and they get scattered off in a random direction.
So it's like a constant game of bumper cars,
Exactly.
but at the atomic level.
At the atomic level, a microscopic bumper car game.
Now it sounds like a very inefficient way to get anywhere.
It is, in a sense.
Right.
But when you average out the motion of a single electron over many collisions, and then you average that over all the free electrons in the conductor, you find that there's a small but consistent average velocity
Okay.
in the direction opposite to the field.
Right.
And that's what we call the drift velocity, VD.
Drift velocity.
And it's a constant average velocity, even though the individual electrons are constantly speeding up and slowing down between collisions.
So the electric field is providing this tiny continuous nudge,
Mm-hmm.
and then boom, they hit an ion,
Right.
get redirected, but then the field immediately starts nudging them again.
Exactly. It's a constant push and pull.
And this constant nudging over countless collisions results in this average drift.
Precisely.
Now, how do we connect this drift to the current that we observe?
Okay, well, let's imagine our cross-sectional area again.
Right.
And because of this drift velocity in a small amount of time, all of the electrons within a certain volume, just upstream of that area, will drift across it.
Okay.
So if we know the number density of those electrons, that's how many electrons there are per unit volume, which we denote as N.
Okay.
And we know the charge of each electron, which is minus E.
Right.
And the drift velocity, we can actually calculate the total amount of charge crossing that area per unit time.
Right.
And that's the current.
Right. So we can relate the microscopic picture
Yeah,
to the macroscopic current.
exactly. And the equation turns out to be I equals N times the absolute value of E times VD times A.
Okay.
So even though the drift speed itself might be really slow, we're
Yeah.
talking, fractions of a millimeter per second.
Right. Super slow.
Super slow.
But if you have a huge number of these charge carriers,
Yes.
you can still end up with a significant current.
Exactly. It's like an ant colony, right? Each ant moves slowly,
Right.
but the sheer number of them allows them to accomplish a lot.
It's amazing.
Yeah.
Now we can actually relate this drift velocity to the electric field.
Yes, we can.
So the force on an electron due to the electric field is minus E times E.
Right.
And using Newton's second law, we can find the acceleration.
Right. So force equals mass times acceleration,
So the acceleration is A equals minus E times E over M.
where m is the mass of the electron.
Right.
Now let's define the average time between collisions.
Okay.
We call this the relaxation time or average collision time.
Okay.
And we denote it by the Greek letter tau.
Tau.
So over that short time interval between collisions,
Yeah.
the electron accelerates, and it turns out that the drift velocity VD is simply minus E times tau over m times E.
Okay, so a stronger electric field
Uh-huh.
leads to greater acceleration.
Right.
And thus a greater drift velocity.
Assuming that tau doesn't change too much.
Right.
Now, if we take that expression for drift velocity
Uh-huh.
and plug it back into our equation for current, and then use the definition of current density,
Right.
we get J equals NE squared over m times tau times E.
And that looks very familiar.
It does, doesn't it?
It's Ohm's law.
It is.
J equals sigma E.
Exactly.
So we've connected the microscopic picture
Yeah.
to the macroscopic observation.
It's beautiful, isn't it?
It is.
How these macroscopic properties emerge from all those microscopic interactions.
Yeah.
Now, we did make some assumptions here.
Right.
We assumed that tau and n are constant and don't depend on the electric field.
Right.
And that holds pretty well under normal conditions, but it does have limitations,
Okay.
which we'll talk about a little later.
Before we do that, I think those examples that we had in the notes
Yes,
are really helpful
they are.
for understanding this stuff.
Absolutely.
So let's start with example 3.1, which was calculating the average drift speed in a copper wire.
Right.
And it was amazingly slow,
It was incredibly slow.
like a tiny fraction of a millimeter per second.
Yeah, much slower than you might imagine.
Yeah, and I think a lot of people think that, electrons are just zipping through wires at the speed of light.
Right.
But that's not the case at all.
Not at all.
Which leads us to that next example, example 3.2,
Okay.
which is, if electrons are moving so slowly, why does my light bulb turn on instantly when I flip the switch?
Right. Good question.
It's not like, the electrons are slowly making their way from the switch to the bulb.
Exactly.
Oh, what's happening?
Well, when you close the circuit by flipping that switch,
Uh-huh.
the electric field is established throughout the entire circuit,
Okay.
almost instantaneously.
Right.
And that electric field acts on all the free electrons everywhere in the wire.
So it's not that a single electron has to make it all the way through.
Right.
It's that the field is set up,
Yes.
and then they all start drifting.
Exactly. It's like turning on a hose that's already full of water.
Right.
You get water out the other end right away, even though the individual water molecules are only moving a short distance.
That's a great analogy.
It is.
The electric field is like the pressure wave in the water, and then the electrons respond to that.
Exact.
Now, another question that came up in that example is, why do electrons acquire a steady drift speed
Right.
instead of, constantly accelerating?
Good question, because you've got this constant force from the electric field.
Right. You would think they just keep speeding up.
You would think so.
So what's going on there?
Well, it comes down to those collisions again.
Those collisions.
So each electron accelerates between collisions, but then it hits an ion
Right.
and loses that momentum and gets scattered.
So it's like it's constantly hitting the reset button and
Exactly.
starting over.
Yeah. And on average, that leads to a constant drift speed.
Right.
It's like a skydiver reaching terminal velocity. They accelerate due to gravity, but then the air resistance balances that out.
Right. So it's a balance between the accelerating force
Uh-huh.
and then the drag.
Exactly.
That's really cool.
It is.
Now, that example also explained how we can have such large currents
Yeah.
with such tiny drift speeds and, the tiny charge of an electron.
Right.
It all comes down to the sheer number of electrons.
There's a huge number of them in a conductor.
Right.
So even if they're each moving slowly collectively, they can carry a lot of charge.
Right. It's like a massive army of slow-moving soldiers, but they can still, get a lot done.
They get the job done.
They do.
Now, another thing that people often get confused about is they think that all the electrons are moving in the same direction,
Right.
but that's not really the case.
So what's going on there?
Well, the drift velocity is really just an average velocity
Okay.
superimposed on top of this much larger random thermal motion.
Mm-hmm.
So it's like you have a crowd of people milling about, but there's a very subtle overall drift of the entire crowd.
Okay, so they're all moving around randomly,
Yeah,
but there's this slight tendency to move in one direction
exactly.
that's creating the current.
Precisely.
That's really cool.
And one more thing about the paths of those electrons.
Okay.
Between collisions, when there's no field, the path is essentially a straight line. But when you apply an electric field, that path gets curved a little bit.
Right, because of that acceleration.
Exactly, due to that acceleration from the field.
Okay, now we've also talked about this term mobility.
Yes,
It sounds like it relates to how easy it is for things to move.
it does.
So what is electrical mobility?
Well, it's essentially a measure of how easily a charged particle can move through a material
Okay.
in response to an electric field.
Uh-huh.
So it's kind of like how responsive a charge carrier is to that electrical push.
Okay.
Quantitatively, it's defined as the magnitude of the drift velocity
Right.
divided by the electric field.
So much equals the absolute value of VD over E.
Exactly.
Right.
And the unit for mobility is meters squared per volt second.
All right, so a material with high mobility
Yeah,
means that the charges can move pretty freely.
exactly. They respond well to that electric field.
Now, we've hinted at this a few times,
We have.
but Ohm's law isn't a universal truth, is it?
No, it's not.
There are times when it breaks down.
Exactly. It's a very useful empirical relationship,
Right.
but it's not a fundamental law of nature,
Right.
like Newton's laws of motion.
So when does it break down?
Well, there are a few ways that we can see deviations from Ohm's law.
Okay.
So one way is that the voltage across the device might not be directly proportional to the current flowing through it.
Right. So if we were to plot voltage versus current, it wouldn't be a straight line.
Exactly. It wouldn't be a straight line.
And why is that?
Well, one reason could be that as current flows through a material, it heats up.
Right.
That's Joule heating.
Joule heating.
And that heat can change the temperature of the material. And if the resistivity of the material is temperature dependent.
Right, which it is for most materials.
It is for most materials.
Then the resistance will also change.
Exactly. So you get this kind of feedback loop.
Right.
More current, more heating change in resistance.
So it's not a simple relationship anymore.
No, it's not.
Okay.
Another type of deviation happens in devices like diodes.
Diodes.
So in a diode, the current flows much more easily in one direction than the other.
Okay.
So if you apply a voltage in one direction, it lets current through.
Right.
But if you reverse the voltage, it blocks the current.
Okay.
So the relationship between V and I depends on which way the voltage is applied.
So it's like a one-way valve?
Exactly, a one-way valve for electricity.
That's really cool.
Yeah, and then there are some materials like gallium arsenide
Okay.
where you can actually have more than one voltage for the same current.
What?
Yeah, it's kind of weird.
So the relationship isn't even one-to-one.
Exactly. It's not a simple one-to-one relationship.
That's what.
Yeah, it leads to some interesting behavior.
So these non-ohmic materials, even though they don't follow the simple rule,
Right.
they're actually super important
They are.
for electronics.
Absolutely. A lot of modern electronics rely on these nonlinear effects.
Okay, so they're the rule breakers, but in a good way.
In a good way, yeah.
Now let's talk a bit more about resistivity
Okay.
and how it varies for different materials.
Right, so we've got this huge range of resistivities
It's enormous.
spanning many orders of magnitude.
Yeah, so let's break it down.
Okay, so at one end, we have conductors,
Right.
primarily metals, things like copper, silver, aluminum.
Uh,
They have very, very low resistivities, so they allow current to.
Chapter 4. Moving Charges and Magnetism.
Okay, so think about this for a sec. You flick a light switch, electrons go zipping through the wires, and boom, light, right.
Yeah.
But then you've got, like, magnets sticking to your fridge. Total different force, it seems. One's about flow, the other's sticky.
Yeah.
But here's the wild part. Not that long ago, like less than 200 years, the link between those two, electricity and magnetism, total mystery. Isn't that crazy?
It really is. I mean, it's so fundamental to everything in our modern world, and yet people back then were basically in the dark ages about it.
It's like not knowing your thumb is part of your hand.
Exactly. And that's exactly why we're diving deep today. You've got a really awesome collection of material here, and it's like our mission to get to the bottom of this whole moving charges and magnetic forces thing.
Yeah, like a crash course.
Yeah.
But without the whole textbook headache.
Yeah.
By the end of this, you'll be dropping science bombs at parties. And the story kicks off, get this, with a total accident. A real, wait, what? Moment in a Danish physicist's lecture hall.
Oh, yeah, Hans Christian Ørsted. A pivotal moment for sure. 1820, what was going on there?
So picture this. Ørsted's in his classroom, summertime, doing a demo with, electric current through a wire, standard stuff, and just kind of chilling nearby. There's a compass needle pointing north like a good compass show.
Right.
But then Ørsted switches on the current and whoop, the needle goes haywire, starts deflecting. Not because he bumped it or anything, but because of that current invisibly flowing through the wire, like the electricity was giving the compass a nudge.
Before that, everyone thought they were totally separate things. Electricity, magnetism, totally unrelated, like as different as baking a cake and, I don't know, skydiving.
Right, different universes. But Ørsted, he's curious, starts poking around, and he finds this pattern, this weird pattern, in how the compass is deflecting. It's not random. It's aligning itself tangentially to an imaginary circle around the wire. Like, picture the wire as the bullseye, and the needle wants to sit right on the edge of one of the rings, always at a right angle to the line going straight out from the wire.
That's what figures 4.1a and b are showing, right? The swirling influence around the wire.
Yep, exactly. And get this. The stronger the current, or the closer the compass to the wire, the bigger the deflection. Like, duh, right? The closer you get to the source, the stronger the effect. But here's the real mind bender. Reverse the current in the wire, boom, compass flips its direction too. Still tangential, but pointing the other way around that imaginary circle. Like, the current's got this magnetic vortex going on.
And then there's the iron filings trick, right? Sprinkle those around the wire, and they line up, making the same concentric circles visible, like magic. Figure 4.1c shows that, doesn't it?
Yeah, exactly. It's like making the invisible visible. So Ørsted's big takeaway, his world-shaking conclusion, is that when charges move, when you've got electric current, they create a magnetic field around them. Mind. blown.
He was a huge deal. It's like realizing, I don't know, vanilla and chocolate ice cream, same base, just served different ways.
Totally. It's a unification moment. And of course, once the word got out, the scientific world went nuts. Your material mentions something like an intense period of experimentation. Everyone's trying to figure this out, what it means.
Yeah, I mean, it set the stage for James Clerk Maxwell, you know, in the 1860s. He's the guy who said, hey, all those laws of electricity and magnetism, they're just different sides of the same coin. Wrote down his famous equations, and boom, the existence of electromagnetic waves predicted, including light. And they travel at, guess what? The speed of light.
Wow, so from a compass needle wiggling to realizing that light is an electromagnetic wave, I mean, that's some serious scientific progress right there.
And then, think about it, building on Maxwell's work, Hertz, Bose, Marconi, all those guys, they figure out radio waves. It's like a direct line from Orsted's lecture hall to, like, your smartphone. And the 20th century, all that crazy tech, it all stems from that fundamental connection.
So in this deep dive, we're going to get into the nitty-gritty, the forces, the fields, how those currents create the magnetic fields in the first place.
Right, and we'll look at some cool stuff like how particle accelerators use magnetic fields to, like, steer these super fast particles.
Oh, and galvanometers, those things that measure tiny currents and voltages, the unsung heroes of electrical measurement.
Definitely. But before we jump into all that, let's just, for the sake of clarity, mention that little visual shorthand your material uses. So when you see a dot, it means the current or field is coming straight out of the page at you. And across, well, that means it's going into the page. Simple but effective, especially for those 3D situations.
All right, so before we get all tangled up in magnetic fields, let's think about something we're more familiar with, electric fields. We've got this idea, right, that a stationary charge, let's call it Q, creates an electric field E around it. And if you bring in another charge, a little pest charge Q, well, it feels a force F. And that force is directly proportional to the field and the charge itself. F equals QE. Easy peasy. And if you've got multiple charges, their fields just add up as vectors, right? Superposition, just like we've seen before.
Right. Now, with Ørsted's discovery, we learned that those moving charges, they don't just create E fields. They create this new field, the magnetic field. We call it B of R. And it varies with position, just like E. And like you said, both E and B are vector fields. They have both strength and direction at each point in space. And they also follow the principle of superposition. Add them all up.
So parallels, right. But here's a twist. Those stationary charges, they're only making E fields. To get a B field, got to have motion, got to have current. It's like, I don't know, they're like a superpower. It needs to be activated. So electricity sitting still, no magnetism. But get those electrons flowing, boom, magnetism unleashed.
Okay, so imagine we've got a charged particle. It's moving with some velocity v, and it zips into a region where there's both an electric field E and a magnetic field B. What happens? What force does it feel?
Well, that's where our friend the Lorentz Force comes in. It's basically the total electromagnetic force on a charge Q, moving with velocity v through both E and B fields, and the equation. Pretty elegant, actually. FEER plus VEBR. Two parts. The electric force, that's the familiar key E, and then the magnetic force, QVEB. Now that little A there, the cross product, that's where things get interesting. It means the direction of the magnetic force isn't always along the magnetic field lines.
Right, let's break it down. First, the charge. Positive charge, negative charge, the force flips direction. You can see that in figure 4.2b. It's like the magnetic field has a positive charges only sign and negatives have to go the other way.
Huh, yeah, magnetic VIP section. And then there's that cross product, VAB. That tells us a few key things. First, the magnetic force is always perpendicular to both the velocity of the particle and the magnetic field. Always a sideways push, never directly along the motion or the field. And to figure out which way that sideways push is, we use the right-hand rule. So you push your fingers along the velocity, curl them towards the field, and boom, your thumb points in the direction of the force. For a positive charge, that is, negative charge. Flip that thumb, figure 4.2a shows that.
Sometimes it's called the screw rule, too. You know, like turning a screw, turn it the way that takes V to B, and the screw goes in the direction of VAB. That's your force direction.
Got it. So even if you've got a crazy strong magnetic field, if the velocity happens to be parallel to the field lines, no force, zero, zilch. The cross product goes to zero, and the particle just keeps cruising. And of course, if the charge isn't moving at all, well, same deal. No velocity, no magnetic force. Got to have motion.
Right. It's like one of those motion sensor lights. Nothing moves, nothing happens.
So now we're talking about Tesla, the unit for magnetic field strength, named after, Nikola Tesla, the genius inventor.
Yeah.
And your material says that 1 Tesla, that's a pretty hefty magnetic field.
It is.
We often see a smaller unit, the Gauss. where 1 Gauss is 10 to the minus 4 Tesla. And just to give you some perspective, the Earth's magnetic field, the one that guides your compass, it's around 0.36 Gauss. So yeah, our planet's got a magnetic field, but it's not going to levitate a frog or anything. For that, you'd need some serious Teslas.
Okay, so we've got a handle on how magnetic fields push on individual charges, but what happens when you have a whole bunch of charges moving together, like in a wire, an electric current?
All right, so imagine a wire, a straight one for now, just like Ørsted used. It's got a cross-sectional area, A, and a length, L, and current's flowing through it, Jerry. That means there's a whole bunch of charges in there, each with a little charge Q, drifting along with an average velocity VD.
Right.
If there are n of these charges per unit volume of the wire, the total number in our length L is, well, n times the volume, which is NLA.
Okay, now put that wire in a magnetic field. B, each of those little charges feels the Lorentz force, right?
Right. And to get the total force on the entire wire, you just add up the forces on all those tiny charges. And that brings us to the equation F, NLA, Q, VD, EB.
But there's a simpler way to write it, right?
Exactly. That whole NQED part, that's basically the current density, J, in the wire. And J times the area, A, well, that's just the total current I. So we can write it as F equals ILEB, where L is now a vector, same length as the wire, pointing in the direction of the current. But remember that B, that's the external magnetic field, not the one the wire's making itself.
And for a bendy wire, a weird shape, you can kind of think of it as a bunch of tiny straight bits, each with a length DL, and just add up the DFIDLAB forces on each little bit.
Okay, let's see this in action. Your material's got this cool example 4.1, the hanging wire. So we've got a wire 200 grams, 1.5 meters long, carrying 2 amps of current. And it's just chilling, hanging in midair, held up by a horizontal magnetic field, B. We need to figure out how strong that B field needs to be to fight gravity.
So for the wire to just hang there, the upward magnetic force has got to equal the downward gravitational force. We know gravity, right? Mass times gravitational acceleration.
Right.
And the current has got to be flowing horizontally perpendicular to the field to get that upward force.
Yeah.
So we set ILB equal to Meller.
Plugging in the numbers, B it'll go 1, U it'll go on 9.8 meters, so it goes to 9.8 meters, 2A, 1.5 meters, which gives us, drumroll, 0.65 Tesla. So yeah, it takes a decent magnetic field to make a wire defy gravity.
And we're ignoring the Earth's magnetic field here, and it's way weaker. To levitate the wire with just the Earth's field, you'd need a ridiculously huge current, like way more amps than your house wiring could handle.
Yeah, probably not a good idea to try that at home. Okay, now let's think about direction. Example 4.2. We've got a magnetic field along the plus y-axis and a charged particle zipping along the plus x-axis. Need to figure out which way the Lorentz force points.
And we've got 2 cases, right? A, an electron, negative charge, and B, a proton, positive charge.
Right. So back to the right-hand rule. Velocity, V, along the plus x-axis. Magnetic field, B, along plus y. Point your fingers along V, curl them towards B, and your thumb points in the direction of VAB, which is plus Z. So for the proton, force is in the plus Z direction. But the electron, negative charge, flips the script. Force goes in the minus Z direction. It's all in the sign of the charge.
Okay, so now we know how magnetic fields push on things. But what happens to the particle itself? What path does it take when it's inside the magnetic field?
Okay, so we know the magnetic force is always perpendicular to the velocity, right? Now think back to Physics 101. When a force acts perpendicular to the motion, it doesn't do any work. It can't speed up the particle or slow it down.
Like trying to push a shopping cart sideways. You can change its direction, but it's not going to go any faster or slower.
Right. So magnetic force can change the direction of a particle's velocity, but not its speed. Big difference from electric fields. They can do work, they can speed things up or slow them down. Magnetic fields, they just steer. They're like the ultimate cosmic traffic cops.
So what happens if the particle's initial velocity is perpendicular to the magnetic field?
Then things get fun. Because that magnetic force is always acting sideways, it acts as a centripetal force. It pulls the particle into a circle perpendicular to the field. It's like a tiny charged particle racetrack. And figure 4.5 shows exactly that.
And what if the velocity isn't totally perpendicular? Like it's got a component along the field lines?
Well, that parallel component, it just doesn't care about the magnetic field. No force on it. So it keeps going straight with constant velocity. But the perpendicular part, still doing its circular dance. So the particle ends up spiraling, moving forward, and going in circles at the same time. Like a corkscrew. Figure 4.6 is a good visual for that.
So we can actually calculate the radius of that circle, right?
Wait, totally. The magnetic force, QVB in this case, because they're perpendicular, is providing the centripetal force, MV phi r. Set them equal, solve for r, and you get r equals MV QB. So Bigger momentum, bigger circle. Stronger field, tighter circle.
And the angular frequency, how fast is it spinning?
That's called the cyclotron frequency. It's given by EQ/QBM. And here's a kicker. It doesn't depend on the speed of the particle, only on the charge, the field strength, and the mass. It's like a cosmic clock, ticking at the same rate no matter how fast the particle's going.
And we can relate that to the regular frequency, AQ to QIA-AET, and the time period T equals 1.
Now for the helix, we've also got to think about the pitch. That's how far the particle travels along the field lines during one loop of its spiral. Basically, it's the parallel velocity times the time for one rotation, so PET equal V2AAQB.
Let's try a numerical example. Example 4.3. We've got an electron moving at 3 times 10 to the 7th meters per second, perpendicular to a magnetic field of 6 times 10 to the minus 4 Tesla. We need to find the radius, the frequency, and the kinetic energy.
All right, time to plug and chug. For the radius, R MVQB equals 9.101 pi 10 kiloeures, 3 LV 10 euros, 1.60, 2 LV 0 C 620 C6 is 0.284 meters, about 28 centimeters. For the frequency, EcoPP euro is 1.60 is COP 622 euro, 204 9.11 out of 10 West 2 tero, which gives us about 16.8 megahertz. And for the kinetic energy, 12 megakerro equals 12, 9.11, so 10 ergo 2 LCers, a 4.1 R 10 lurs, that's about 2.56 key.
Okay, so we've seen how magnetic fields push and pull on charges, but how do currents actually create those magnetic fields in the first place?
Enter the Biot-Savart Law. It's kind of like Coulomb's law for magnetic fields. Coulomb's law tells you the electric field from a charge. Biot-Savart tells you the magnetic field from a tiny piece of current, a current element.
Like the smallest building block of a magnetic field.
Exactly. So picture a wire, XY, carrying a steady current I, just like in figure 4.7.
Oh, no.
Now focus on a tiny, tiny piece of that wire, length dl. Biot-Savart tells you the teeny magnetic field dB made by that little piece at some point p in space r away.
Right, and there's an angle between that little piece of wire and the vector going to the point P.
Okay. So Biot-Savart says dB is proportional to the current, the length of that tiny piece, and the sine of that angle. And it's inversely proportional to the square of the distance. Sound familiar? Inverse square law.
Yep. The full equation in vector form is dB, all a quote, for I dLs r or.
Right, and that's the permeability of free space.
Yeah.
And that EL4 part, that's exactly 10 to the minus 7 Tesla meters per ampere. Always.
And just like the other right-hand rules, the direction of dB comes from that cross product, dLER. Curl your fingers from dl to r, thumb points in the direction of dB. And if the point P happens to be right along the line of that little piece of wire, dB is 0 at that point.
Okay, so Biot-Savart and Coulomb's law, they've got some things in common. They're both long range, both follow that inverse square law. And this superposition principle works for both. You can just add up the fields from multiple sources.
But there are some big differences too, right?
Definitely. The electric field, it comes from a scalar source, the charge, and it points directly towards or away from that charge. But the magnetic field, it's from a vector source, the current element, and its direction is perpendicular to both the current element and the vector pointing to where you're measuring the field.
Oh.
And don't forget that sine of the angle in Biot-Savart.
That's a key difference for sure.
Oh, and another crucial thing, there's this deep connection between the torus, the permittivity of free space, and c, the speed of light. The equation's 1 AC pi T L day. It's a beautiful reminder that electricity and magnetism are basically two sides of the same coin, and light's the thing connecting them. Your material says that in the SI system, A is defined as exactly 4 ag 10 ATMA. And once you know that and the speed of light, boom, you've got a scorch. It's all beautifully interconnected.
Absolutely. So let's look at an example. Example 4.4. We've got a teeny current element, R's name, sitting at the origin. It's got a length of 1 centimeter and carrying 10 amps of current in the positive x direction. We got to find the magnetic field it makes at a point on the y-axis half a meter away.
So our DL is along x and our point P is along y. The vector R going from the origin to P is 0.5 meters to us. The angle between DL and R, 90 degrees, so sin it is 1. Plugging all that into Biot-Savart, dB equals 10 euro, 10 air, 0.01 meters R, 0.5 meters, which gives us 4 times 10 to the minus 8 Tesla.
And the direction.
For that, we look at the cross product, DLAR, which is I or air, and that's in the co-direction, or the plus Z axis. So our tiny current element makes a magnetic field of 4 times 10 to the minus 8 Tesla in the plus Z direction at that point. Not huge, but definitely there.
Now, in theory, we could use Biot-Savart to calculate the field for any arrangement of currents, but sometimes the math gets pretty messy. So let's look at a more organized setup, a circular current loop.
A classic. Okay, imagine a wire loop, lying flat in the YZ plane, centered at the origin, radius r, with a steady current I flowing through it. You can see it in figure 4.9. We want to find the magnetic field at a point P on the x-axis, x away from the center. Important problem, lots of applications.
So we break it down, right? Think about a tiny piece of that loop, dl/r. Biot-Savart tells us the dB from that little piece at our point P.
And the distance from that piece to P is x plus r run. And since our loop's in the YZ plane, dl is always perpendicular to the part of r that's in that plane. So the magnitude of dl(r) is just dl times r, or dl x plus r. So dl is nearest plus r run x plus r, ILO x plus r run. But that dB has components, right? One along the x-axis, dBx, and one perpendicular to it, dBl.
Right, but because of the symmetry of the loop, the perpendicular components from opposite sides of the loop cancel out.
Yeah, it's like a tug-of-war where both sides are equally strong. So the only thing left is dBx. And from the geometry, dBx equals dB cos, where phi is the angle between r and the x-axis. Looking at the figure, we can see the cos are r, x cos plus r.
So we substitute and get dBx plus RAD, Rx's plus RO. To get the total field B at point P, we got to integrate dBx around the whole loop. And the integral of dl is just the circumference, 2r. So we end up with B dxi ROs, 2x plus RO equals r over r.
And at the center of the loop, dBec as A.
Ah, that simplifies things. B, r over 2 over 1 apart plus r over. Is r over is r over o. So at the center, the field is proportional to the current and inversely proportional to the radius. Simple and useful.
And the overall picture of the magnetic field lines, they form these closed loops, right, in figure 4.0. And we can use that right-hand rule again to get the direction. Curl your fingers in the direction of the current, and your thumb points in the direction of B. It's almost as if the loop acts like a tiny bar magnet. Okay, let's do another example. Example 4.5. We've got a wire with 12 amps of current. It's bended to a half circle, radius of 2 centimeters. Got to find the magnetic field at the center of that half circle.
First, let's think about the straight bits of the wire. For any tiny piece, dl, along those straight parts, dl and the vector r to the center are either parallel or anti-parallel. And the cross product is 0 when that happens. So those straight bits, they don't contribute anything to the field at the center.
Nice. So it's all about that half circle.
Yeah.
But how does its field at the center compare to a full circle with the same radius and current?
Well, every dl on the half circle is perpendicular to r pointing to the center. So sin is 1. And if you use the right-hand rule, the dB from each little piece points in the same direction. They all add up. And the length of a half circle is half the length of a full circle, right? So the total field from the half circle is exactly half the field from a full circle. And we know the full circle's field at the center is I to R. So for the half circle, it's B semicircle 12, IQR, I 4RR. Plugging in our numbers, we get about 1.9 times 10 to the minus 4 Tesla. And if you use the right-hand rule, you'll see it points into the page.
Okay, let's look at a tightly wound coil now. Example 4.6. We've got 100 turns, radius 10 centimeters, carrying 1 amp. Got to find the field at the center.
Because it's tightly wound, we can think of each turn as a separate loop, all with the same radius and current. And at the center, the field from each loop points in the same direction. So we just add them up. We know the field at the center of a single loop is B single loop equals I to R.
Right.
So for n turns, B total and B single loop equals n I to R. Plugging in the numbers, we get B total I 100 for x 10 year TMA 1A, 2.1 emitter is 2P 10 year to SES.
So more turns, stronger field. Makes sense. Now, we've been using Biot-Savart to figure out these fields, but there's another way. Ampere's circuital law.
Right, and it's often easier, especially when things are symmetrical. Instead of looking at tiny bits of current, it looks at the total current enclosed by a loop, an Amperean loop. It says the integral of the magnetic field around that loop is equal to aura times the enclosed current. BEODL equals aura I.
Sounds kind of like Gauss's law for electric fields, right?
Exactly. Gauss's law relates the electric field on a surface to the charge inside. Ampere's law relates the magnetic field on a loop to the current inside. Both super useful when things are symmetrical. And sometimes you can simplify that integral to BL, i.e. where B is the field strength, L is the length of a part of the loop where the field is constant and tangential, and IE is the enclosed current.
Let's see it in action. The classic example. An infinitely long straight wire carrying current I. We want to find the field at a distance r from the wire.
Okay, so we pick our Amperian loop to be a circle of radius r centered on the wire in a plane perpendicular to the wire. Because of symmetry, the magnetic field is tangential to that circle and has the same strength all the way around.
Right, so the integral of BO just becomes B times the circumference, 2r,
Yeah.
and the enclosed current is just I.
Exactly. So Ampere's law gives us B to R, it equals I. Solving for B, we get B equals I to R. Same result as Biot-Savart, but much easier.
So the magnetic field lines around a straight wire are circles, their strength drops off as you move away, and the direction is given by the right-hand rule. Point your thumb in the direction of the current, and your fingers curl in the direction of the field, just like those iron filings showed.
Exactly.
And even though it's an infinitely long wire, the field is perfectly finite at any distance from the wire. No magnetic singularities here.
Right. And remember, Ampere's law and Biot-Savart, they're both describing the same thing, the connection between currents and fields. It's just that Ampere's law is a more powerful tool when things are nice and symmetrical.
Okay, example 4.7. We've got a wire with radius A carrying current I evenly spread out over its cross-section. We want to find the field both inside and outside the wire.
Outside, where R is greater than A, we can use the same circular Amperian loop as before. The enclosed current is still I, so we get B 2R equals I, and therefore B E rho 2R. The field acts like all the current squeezed down the center of the wire, and it gets weaker as you move away.
But inside the wire, where is less than A, things get trickier.
Right, because our Amperian loop now only encloses part of the current. Since the current is uniform, the enclosed current, i.e., is just the total current times the ratio of the loop's area to the wire's area, i.e. I, or Ri, or Ra.
Okay.
So Ampere's law gives us B to R, i.e. OR. And solving for B, we get B RAOR. So inside the wire, the field increases linearly as you move away from the center. And at the center, R is yield 0, so the field is 0 there.
Cool. The way the current spread out affects the field inside the wire. And figure 4.14 shows this, how the field changes as you move in and out.
Exactly. Now, let's move on to something a bit more complicated, but super useful. Solenoids.
Ah, solenoids. You find them everywhere. They're basically coils of wire. So imagine you take a long wire and wind it up into a helix, a coil with lots of turns close together. If it's much longer than it is wide, we call it a long solenoid. And each turn of the wire, well, that's like a little current loop.
And the total field is just the sum of the fields from all those little loops.
Right. And to keep things neat and tidy, they usually use enameled wire, so the turns don't short-circuit each other. Now, figure 4.15 shows the field lines from a solenoid. Inside, near the center, they're pretty straight, parallel to the axis, and evenly spaced, meaning a nice uniform field. Outside, they spread out and get weaker.
And for an idealized long solenoid, we can make a simplifying assumption, right? The field outside is basically 0, and the field inside is perfectly uniform along the axis.
Perfect. And to calculate that field inside, we can use our friend Ampere's law again.
Right. We imagine a rectangular loop, ABCD, like in figure 4.16. One side, length h, is inside the solenoid, parallel to the axis. The other side's outside, where the field's 0. The other two sides are perpendicular to the axis. Now we walk around this loop, adding up B, U, T, L.
Okay.
On the side outside, B is 0, so that part of the integral is 0. On the 2...
Chapter 5. Magnetism and Matter.
It's amazing when you really think about it. Magnetism is just everywhere.
Absolutely, yeah.
I mean, from like massive, huge galaxies, right? All those stars swirling around, all held together by magnetic forces,
Right.
to like the tiniest little atoms.
Yeah?
Magnetism is just woven into the fabric of the universe. It's been around like way before we were even a twinkle in the cosmic eye. I mean, planet Earth, our own home, has had a magnetic field for billions of years, you know? It's pretty mind-blowing.
Yeah, it is. And it's interesting. The word magnet itself, it takes us back to, like, ancient Greece,
Oh, yeah.
around 600 BC, to a region called Magnesia.
Huh.
And that's where people first stumbled upon these naturally occurring magnetic rocks. You know, they were like, whoa, what's going on with these stones?
Yeah.
But the real leave-in understanding, the real aha moment that came much later in the early 1800s and 19th century.
Okay.
And there were these brilliant scientists like Ørsted, Ampere, Biot-Savart, a real dream team of physics, you might say.
Right.
And they figured out the connection between electricity and magnetism. They showed that moving electric charges, what we call electric currents,
Right.
actually create magnetic fields. So electricity and magnetism, they're not separate things. They're two sides of the same coin, fundamentally.
Yeah, exactly. And that's what we're diving into today, this whole amazing world of magnetism. We've got some really cool material to work with, and our mission, if you will.
I like it.
is to unpack these fundamental ideas, see how they all fit together, how they work.
That's like a plan.
Now, I'm sure a lot of you out there already know some of the basics, right? I mean, Earth is a giant magnet. You've got your fridge magnets, always a classic. You know that opposite poles attract, like poles repel. You can't just break a magnet in half and get a lone north pole or a lone south pole. And who hasn't tried to, like, magnetize a paperclip by rubbing it with a magnet?
Oh, yeah, the classic childhood experiments.
Right. It's fascinating stuff, even at that basic level.
It is.
Yeah.
But what I think is really elegant is the sort of the theoretical framework behind it all, the way these basic ideas connect to these deeper principles that govern how magnetism works at all scales.
Yeah, for sure.
So maybe let's start with something familiar, something we can all visualize, a bar magnet.
The classic bar magnet. Okay, yeah. You know, if you've ever sprinkled iron filings around a bar magnet, you've seen that awesome pattern they make, right?
Oh, yeah.
Like these invisible lines of force coming out of the magnet. That pattern really shows you that a bar magnet has these two distinct regions, two poles, the North Pole and the South Pole.
Right.
It's kind of like the positive and negative ends of a battery, but, you know, magnetically. And like those early navigators figured out with their compasses, if you hang a bar magnet so it can spin freely, what happens?
It lines up.
It aligns itself with the Earth's magnetic field, roughly pointing north-south.
Yep.
Like it's trying to find its magnetic home.
Exactly. And that alignment, you know, with those compasses and the bar magnet, it really gives us a way to start visualizing these things called magnetic field lines. Think of them as like a map of the magnetic force that the magnet creates in the space around it.
Okay, yeah.
They show us the direction of that force and also how strong it is at any point.
Yeah.
Now, a key difference between these magnetic field lines and electric field lines, which you might have heard about,
Right.
is that magnetic field lines, they don't start and end on poles in isolation. What's crucial about their shape?
Well, they form these continuous closed loops. They don't just like pop out of the North Pole and disappear into the South Pole. They curve around and go right back through the magnet itself, completing a full circle.
Right. That's a big difference.
Yeah, that's different from electric fields, which do start on positive charges and end on negative charges.
Yes.
And another cool thing, if you were to put like a tiny little compass needle at any point along one of these magnetic field lines, the needle would point in the direction of the line.
Yeah.
That's the direction of the magnetic field right there.
At that spot.
And where the lines are bunched up really close together, like near the poles,
Yeah.
the magnetic field is strong.
More intense.
Where they're spread out, the field is weaker. Kind of like a crowd, a denser crowd means, you know, more people packed into the same space.
Yeah. More push and shove.
Exactly. More magnetic power, I guess you could say.
That's a good analogy.
Oh, and one last important thing. These magnetic field lines, they will never, ever cross each other.
That's right.
Because if they did, a compass at that point would be totally confused.
Yeah.
Trying to point in two different directions at once.
Magnetic chaos.
Total magnetic anarchy.
Exactly. That non-crossing rule, that's vital. You know, if you want to have a clear, consistent definition of the magnetic field's direction, you got to have that rule. And you can even, you can map these magnetic field lines yourself, you know, at home or wherever. Just take a compass and place it around the magnet, mark where the north end of the compass points, and then just connect the dots.
Simple.
Yeah. It's a really cool hands-on way to make this sort of abstract concept of a magnetic field feel a bit more real.
Totally. So now let's bring back that idea we touched on earlier about electricity and magnetism being connected. You mentioned Ampere's hypothesis, which basically says that all magnetism at its core is the result of circulating electric currents. Like it's all just tiny little electric loops doing their thing.
It's a really powerful idea, and it turns out it's a super useful way to think about even a simple bar magnet. If you look at the pattern of those magnetic field lines around a bar magnet, and then you compare that to the field lines around a solenoid, which is that coil of wire we talked about, you'll notice that they look incredibly similar, especially from a distance.
Yeah, you're right. It's almost like the bar magnet is just a super, super dense collection of these tiny microscopic solenoids all packed in there and aligned.
That's exactly the analogy. And here's another thought experiment. You know, one of those thought experiments that physicists love.
Yeah.
Imagine cutting a bar magnet in half. What do you get?
Two smaller magnets.
You get two smaller bar magnets.
Okay.
Each one still has a north and a south pole.
Yeah.
You never end up with just a lone north or a lone south. You always create two new magnetic dipoles.
Right, right.
Now, imagine cutting a solenoid in half.
Okay.
You get two shorter solenoids.
Uh-huh.
And assuming, hypothetically that you keep this circuit connected, the current's still flowing.
Right.
Each of those shorter solenoids still creates its own magnetic field, and it still has two poles. It's like this analogy holds up even when you start chopping things in half.
Yeah, that's a really neat way to visualize it.
It is. And even if you were to take a compass needle and wave it around a bar magnet and then wave it around a current-carrying solenoid with a similar field strength, the compass needle would behave pretty much the same way in both cases. It would point in similar directions.
So, is it fair to say that the magnetic moment of a bar magnet, which is like a measure of its overall magnetic strength and orientation, is essentially the combined effect of all these teeny tiny atomic current loops inside it?
Yeah, in a way, that's a good way to think about it. And we could even back this up with some math.
Oh, fun.
Always fun. It turns out that the magnetic field along the axis of a finite solenoid, when you're far enough away from it, has the exact same mathematical form as the magnetic field along the axis of a bar magnet.
Wow.
And there's an equation for this. It's B equals 4 times 2 meter, where m is the magnetic moment and r is the distance. So from a distance, a bar magnet acts just like an equivalent solenoid producing the same field. It's like they're wearing the same magnetic disguise.
I love that. Magnetic disguise. Okay, so we've got our bar magnet, our magnetic dipole. Now, what happens if we take this bar magnet and stick it into a uniform magnetic field? Like, imagine the Earth's magnetic field, but perfectly even in strength and direction everywhere.
Good question. So just like a compass needle that always wants to align itself with the Earth's field and point north,
Right.
our little magnetic dipole, the bar magnet, it'll experience a torque.
A torque.
Which is a twisting force that tries to align its magnetic moment with the direction of that external field.
Okay, yeah.
Now, the strength of this twist, it depends on a few things. How strong the magnet is, magnetic moment, let's call it M. How strong that external field is, we'll call that B. And the angle between the magnet's moment and the field direction. The formula for this torque is MET, or if you just care about the magnitude of that twist, you can write it as MBC.
So if I'm picturing this right, when the magnet's trying to point sideways to the field at like a 90-degree angle, that's when the torque is strongest. Right. It's really trying to flip around. But when it's already lined up with the field, either pointing the same way, 0 degrees, or the opposite way, 180 degrees, the torque is 0 because it's either happy where it is or perfectly opposed.
Exactly. You've got it. And just like we have potential energy stored in an electric field when you move charges around,
Right.
a magnetic dipole in a magnetic field, it also has potential energy. We call it magnetic potential energy. And it's given by the formula U sub as Jeff MB, which you can also write as U sub Nas MB cos. Now, let's think about stability for a second. When is this potential energy at its absolute lowest?
Well, that would be when the cosine of the angle is at its maximum, right? Which
Yeah.
happens when the angle is 0 degrees.
Yeah.
That means the magnetic moment is perfectly aligned with the external field. And that makes sense intuitively, like a compass needle settles down pointing north because that's its lowest energy state. It's like magnetically comfortable there.
That's exactly right. That's what we call stable equilibrium. You can give it a little nudge, and it'll just swing right back to that aligned position.
Right.
Now, what about when the angle is 180 degrees? When the magnetic moment is pointing exactly opposite to the field? What's the energy like then?
Well, the cosine of 180 degrees is -1, so the potential energy would be at its maximum. That sounds like a pretty unstable situation.
Yeah, that's unstable equilibrium. It's like trying to balance a ball perfectly on the very top of a hill. Any tiny push will send it rolling down to a lower energy state.
Yeah, I get it. Makes total sense. Okay, now remember those examples we had in our material about cutting a bar magnet?
Oh, yeah. Good ones.
We mentioned it before, but the example specifically says that when you cut a bar magnet, you get 2 smaller magnets, each with its own north and south pole. It's like you can never isolate a single magnetic pole no matter how many times you slice and dice it.
Exactly. It's a fundamental aspect of magnetism. Now, another example talked about a magnetized needle in a uniform magnetic field. It experiences a torque, that twisting force, but no net force. Why is that?
Well, in a uniform field, the force on the north-seeking end of the needle and the force on the south-seeking end, they're equal in strength, but opposite in direction.
Right.
So they cancel each other out in terms of pushing or pulling the whole needle in one direction. But because those forces are acting at different points on the needle, they create that twisting effect, the torque.
Exactly. Now, what about an iron nail? When you bring it near a bar magnet, it experiences both a force and a torque. Why does it get pulled towards the magnet in addition to twisting?
Ah, because unlike that uniform field we were talking about, the magnetic field from a bar magnet isn't uniform. It gets weaker as you move away from the magnet.
Yes.
So the part of the iron nail that's closer to the magnet feels a stronger force than the part that's farther away. That difference creates a net force that pulls the whole nail towards the magnet. And since iron is attracted to both poles of a magnet, no matter which end you bring near the nail, it always gets pulled in.
Right. It's always an attractive force.
Yeah. Plus, that non-uniform field can also induce a temporary magnetic moment in the iron nail, making it act like a tiny magnet itself. And that induced moment interacts with the field to create the torque, trying to align itself.
You got it. It's like the nail briefly becomes a magnet, and then it wants to align itself with the fields of the bigger magnet.
Cool. Okay, and there was another question that came up about whether every magnetic configuration has a clear north pole and south pole. The answer was no, and it mentioned examples like a toroid, that donut-shaped coil of wire, or an infinitely long, straight wire carrying current. What makes them different from a bar magnet in terms of poles?
Good question. So in those cases, the toroid and the infinite wire, the magnetic field lines, they form closed loops, but they don't originate or end at those specific localized points that we would call north and south poles.
Okay.
Like in a toroid, the magnetic field is confined entirely within that donut shape, looping around and around. And with the infinite wire, the field circles around the wire in these concentric rings. They create magnetic fields for sure. In fact, a toroid has an overall magnetic moment, but their fields aren't structured in a way that gives them those distinct north and south poles that emerge from the ends of a bar magnet.
Right. Yeah.
So it really comes down to the overall shape and configuration of the magnetic field.
Got it. Makes sense. And the last example in that section was a real brain teaser. It asked how you could figure out if one or both of two identical iron bars were magnetized using nothing but the bars themselves. No external magnets allowed.
Ah, that's a good one.
So how do you do it?
Well, the trick is to look for repulsion.
Repulsion, okay.
So you take one end of bar A, bring it close to one end of bar B. If you feel a clear repulsive force, a push, then you know for sure that both bars must be magnetized.
Why is that?
Because an unmagnetized iron bar will always be attracted to a magnetized one, no matter which ends you bring together.
Oh, right.
Repulsion only happens between poles of two actual magnets. If you feel a push, you got two magnets facing each other with the same pole.
Okay.
Now, if you only ever feel attraction, no matter which ends you try, then you know at least one of them isn't magnetized.
Right, because if they were both magnets, you'd find some combination of ends that would repel each other.
Exactly. To figure out which one is magnetized in that case, you can use the fact that a magnet's field is strongest at its poles.
Right.
So pick up one bar and touch one of its ends to the middle of the other bar.
Okay.
Then try touching it to the ends of the other bar.
Got it.
If you feel a noticeably stronger pull when you touch the ends compared to the middle, then the second bar you are touching is the magnet.
Makes sense.
If you feel a similar attraction, whether you touch the ends or the middle, then the first bar you picked up is the magnet, because an unmagnetized bar will be equally attracted to any part of a magnetized bar.
Ah, clever. I like that.
It's all about using the variation in field strength. It's a fun little magnetic puzzle.
Totally. All right, so we've really thoroughly explored the bar magnet. Now, our material brings up this interesting connection between magnetism and electrostatics. They call it the electrostatic analog. What is that all about?
Well, this is where you really start to see the interconnectedness of physics. The equations that describe electric dipoles, like those formed by a positive charge and a negative charge separated by a distance.
Right.
If you compare those equations to the equations for magnetic dipoles, like our bar magnet with its north and south poles, you'll find some really striking similarities in their structure. It's almost like there's a little dictionary where you can just swap out certain terms for their magnetic counterparts and get equivalent equations.
That's cool.
Yeah, it's like a secret code the universe is using.
I like that.
For example, you can replace the electric field, E, with the magnetic field, B, the electric dipole moment, P, with the magnetic dipole moment, M. And that constant 1 euro that shows up all the time in electrostatics, you swap that with Faraday and magnetism.
So if I already know the equations for, say, the electric field created by an electric dipole, I can just make those swaps and instantly get the equations for the magnetic field produced by a bar magnet. That's pretty handy.
Exactly. And that's precisely how we get the equations for the equatorial field and the axial field of a bar magnet when you're far away from it.
Okay.
The equatorial field is given by B sub E sub, Pussy 4, and the axial field is B sub A sub, 4 2-meter Padan. If you've seen the equations for an electric dipole, these will look very familiar.
Yeah, that's neat.
Yeah, and our material even has this helpful table that lays out this analogy side by side. It compares things like permeability, dipole moment, those axial and equatorial fields, the occasions for torque and energy. When these dipoles are in an external field, both electric and magnetic, it really highlights how, even though these two forces seem different on the surface, they actually share a fundamental mathematical structure.
Yeah, it's like they're following the same blueprint, just with different labels.
Exactly. And these analogies, they're not just fun mathematical exercises. They can give us valuable insights into one phenomenon by understanding the other. And sometimes they even point to deeper connections in the laws of physics. Now, there was an example in our material with two interacting magnetic needles, labeled P and Q. They were arranged in several different configurations. What do you remember about the key ideas in that example?
Oh yeah, that one. So one needle, P, was fixed in place, and the other one, Q, was placed in 6 different spots around it with different orientations.
Yeah.
And the question was about equilibrium, like in which of these arrangements would needle Q be stable, unstable, or not in equilibrium at all? And it all came down to the potential energy of needle Q in the magnetic field created by needle P.
Right.
Remember, systems in nature tend to want to be in their lowest possible energy state.
Always seeking that low energy state.
So stable equilibrium happens when the magnetic moment of Q, we'll call it M sub Q sub, is pointing in the same direction as the magnetic field produced by P at that location, B sub P sub, because that's the arrangement with the minimum potential energy. Unstable equilibrium is when M sub Q sub is pointing exactly the opposite way to B sub sub, that's the highest energy state.
Okay.
And if M sub Q sub is at any other angle relative to B sub sub, then there will be a torque trying to twist it into alignment, so it's not in equilibrium at all. It'll want to move.
And the configuration label PQ6 in the diagram, do you remember that one? Where needle Q was placed along the axis of P and pointing in the same direction. That was the one with the lowest potential energy, right?
Yes, that was the most stable arrangement.
Yeah.
It's like those two magnetic dipoles just want to snuggle up end to end with their opposite poles facing each other. That minimizes their overall magnetic energy.
Exactly. Now, we've talked a lot about the similarities between electric and magnetic fields, especially with these dipole analogies. But there's a really fundamental difference between them, and that leads us to Gauss's law for magnetism.
Ah, Gauss's law, always a big one in physics. So for electricity, Gauss's law tells us that if you enclose a charge within an imaginary closed surface, the amount of electric field passing through that surface is directly proportional to the amount of charge inside. But for magnetism, it's different. Gauss's law for magnetism says that the total magnetic flux, think of it like the net number of magnetic field lines passing through any closed surface, is always zero. Always. It's represented by this equation, sub equals 0. What's the big deal about that 0?
That 0, it tells us something really profound about magnetic fields. It's a direct consequence of the fact that, as far as we know, isolated magnetic poles, those hypothetical magnetic monopoles, just don't exist in nature.
Interesting.
Unlike electric charges, where you can have a positive charge all by itself or a negative charge on its own, magnetic poles always come in pairs, a north and a south, always together. So if you imagine any closed surface around a magnet, no matter what shape, the number of magnetic field lines going into that surface is always equal to the number of lines coming out. There's no starting point, no ending point for those lines within that surface. No magnetic monopoles hiding in there.
Okay, yeah.
It's like every magnetic out has a corresponding magnetic in.
So if we go back to those pictures of the closed surfaces around a bar magnet or a solenoid, it makes perfect sense. Every line that enters the surface on one side has to exit on the other side because there's no source of those lines, no lone pole trapped inside. It all just loops around continuously.
Precisely. And this is where it's really different from Gauss's law for electricity, where if you enclose a net charge within your surface, you do get a non-zero net electric flux.
Right, right.
That difference highlights the fundamental distinction between these two forces. Now, do you remember those examples in the material of incorrectly drawn magnetic field lines?
Oh, yeah, those were good for clarifying things.
They were. Let's look at a couple of those to really solidify our understanding of Gauss's law for magnetism and what it tells us. So the first wrong example showed magnetic field lines radiating outwards from a single point.
Right.
It was labeled as wrong for magnetism, but correct for the electric field of a long charged wire.
Yeah.
What's the key difference there?
Well, those radiating magnetic field lines from a point would mean there's a net outward flux from that point. Like it's a source of magnetic field, a magnetic monopole. And Gauss's law for magnetism says no way to that. But a long charged wire, that does act as a source of electric field lines. And that picture, with the lines radiating out, that's consistent with Gauss's law for electricity, which connects the flux to the enclosed charge. So the takeaway is no magnetic monopoles, no isolated sources of magnetic field.
Precisely. You nailed it. Another incorrect drawing showed lines crossing each other and forming closed loops in empty space, far away from any magnets or currents. What's wrong with that picture?
Okay, two main problems there. First, remember, magnetic field lines and electric field lines too, by the way, they can never cross.
Right.
Because if they did, it would mean that at that crossing point, a compass needle or a charged particle moving through that field would experience a magnetic force in two different directions at once.
Which is impossible.
Which is impossible. It just doesn't work like that. The magnetic field has one unique direction at every point in space. And second, static magnetic field lines can't just spontaneously form closed loops out in empty space.
Yeah.
A closed loop of magnetic field has to enclose an electric current. That's a fundamental principle related to Ampere's law, which connects magnetic fields to the currents that create them.
You've got it.
And then there was the solenoid example where it showed perfectly straight magnetic field lines inside the solenoid.
Yeah.
And then they just abruptly stopped at the ends with no field lines looping back around on the outside.
Yeah.
That was
Good.
wrong too, and it said it violated Ampere's law. The lines have to curve outwards from the ends and form those closed loops. That really emphasizes the no magnetic monopoles rule, right?
Exactly. Those field lines have to close on themselves. They can't just start and stop abruptly.
Yeah.
And that fringing effect you see in real solenoids,
Right.
where the field lines do curve out at the ends, that's unavoidable. And it's consistent with Ampere's law, which says those currents in the wire create the field.
Yeah. I remember now. There were some correct examples too, which really helped to solidify the concepts for me. Like the field lines inside a toroid, all nicely confined in those closed loops within the donut shape. And the field lines for the bar magnet, both inside and outside, showing those continuous loops and highlighting that zero net flux around the poles that Gauss's law talks about.
Right.
And then there were more incorrect ones to compare, like those field lines seeming to come from a charged plate that's electrostatics, not magnetism.
Yeah.
And those perfectly straight field lines between the poles of a magnet, where in reality you get that fringing effect. It was a good exercise to see the right and wrong examples side by side.
It really drives home those fundamental rules.
It does. Okay, and the last example in that section had a bunch of true or false statements about magnetic fields.
Oh yeah, those were fun.
One of them said that magnetic field lines don't represent the lines of force on a moving charged particle. Why is that true?
Well, think about the formula for the magnetic force on a moving charge.
All right.
It's F equals QV as B,
Mm.
where Q is the charge of the particle, V is its velocity, and B is the magnetic field. That cross product, VAB, it means the resulting force is always perpendicular to both the velocity of the charge and the direction of the magnetic field.
So the force isn't acting along the field lines, it's acting at a right angle to them.
Exactly, they're perpendicular.
Yeah.
Then there was that interesting statement about what would happen if magnetic monopoles actually existed.
Mm.
How would Gauss's law for magnetism have to change?
Oh, yeah. It would have to become a lot like Gauss's law for electricity. Instead of the net flux always being zero, it would be proportional to the total magnetic charge the monopole is enclosed within that imaginary surface. So the equation would look something like BDS times the enclosed magnetic charge, where is that permeability of free space constant we've seen before.
That's right. A simple modification to account for those hypothetical monopoles. And then there was one about how a bar magnet doesn't exert a torque on itself.
Right.
But a current-carrying wire can exert a force on another part of the same wire unless it's perfectly straight. What explains that difference in self-interaction?
Well, in the bar magnet, the magnetic field at any point inside is created by all the other parts of the magnet, not by that specific point itself. So it can't exert a force on itself through its own field. It's like trying to lift yourself up by pulling on your own shoelaces. It just doesn't work.
I like that analogy.
But in a wire with a current flowing through it, different parts of the wire are creating magnetic fields, and those fields can then push or pull on other current-carrying segments of the same wire.
Right.
Now, in a straight wire, those forces tend to cancel out overall, so there's no net force or torque on the wire as a whole.
Yeah.
But if you bend the wire into a loop or some other shape, then those forces don't necessarily balance out anymore, and you can get a net force or torque acting on the wire.
Excellent explanation. And the last statement in that set was, a system with zero net electric charge can still have a net magnetic moment. How is that possible?
Well, think about an atom, right? You've got electrons whizzing around the nucleus.
Uh-huh.
Each electron has a negative electric charge, and its orbital motion is essentially a tiny electric current loop.
Yeah.
That loop creates its own tiny magnetic field and has a magnetic moment.
Right.
Now, even if the atom as a whole is electrically neutral, meaning it has equal numbers of positive protons and negative electrons, the magnetic moments from all those electrons might not perfectly cancel each other out.
Right.
So some atoms can end up with a net magnetic moment because of the way their electrons are arranged and moving. And that's actually the basis for paramagnetism, which we'll get to next.
Exactly. It all ties together beautifully. Okay, so we've built a solid foundation here with bar magnets, magnetic field lines, Gauss's law, those dipole analogies. Now let's move on to how different materials behave when you stick them in a magnetic field. This takes us to the concepts of magnetization and magnetic intensity.
Okay, so let's say you have a chunk of some material. Magnetization M is basically a measure of how strongly that material has been magnetized.
Right.
More precisely, it's the net magnetic moment per unit volume of the material. So if all the tiny little atomic magnetic dipoles inside that material are lining up in roughly the same direction, then the material will have a non-zero magnetization. It's like a measure of how magnetically organized the material is at the microscopic level. And we measure magnetization in amperes per meter.
Perfect. Now let's think back to our solenoid friend. We know that a long solenoid with n turns of wire per unit length carrying a current I creates a magnetic field inside. Barrow, which is given by B rho equals Ni. E, remember, is the permeability of free space.
Yep.
Now what happens if we take that empty solenoid and fill its core with some magnetic material? What happens to the magnetic field inside?
Well, doesn't the magnetic field inside either get stronger or weaker, depending on the material?
Chapter 6. Electromagnetic Induction.
All right, welcome to another deep dive. You know how this works. You send us the sources, and we dive deep.
That's right. We get to the heart of what's interesting, what's important, no distractions.
Exactly. And this time, it's all about something truly fundamental. The link between electricity and magnetism. Specifically, we're talking about electromagnetic induction.
Ah, yes. The discovery that changed the world. You sent over some introductory physics material, and, well, I think we've got a fascinating journey ahead of us.
Absolutely. So our mission, should we choose to accept it, is to help everyone understand how these two things, electricity and magnetism, once considered totally separate forces of nature, how they were found to be so deeply interconnected.
Right. And how that discovery revolutionized, well, pretty much everything. We're talking technology, the way we live.
Right.
It all traces back to this fundamental connection.
It really does. I mean, think about it. For centuries, people thought electricity and magnetism were completely unrelated.
Like two ships passing in the night.
Yeah.
No interaction whatsoever.
Exactly. Each doing its own thing. But then along comes the 19th century and, well, the scientific world gets a serious jolt.
A literal and figurative jolt.
That's a good one. But you're right. Experiments by Ørsted, Ampere, and others, they really started to pull back the curtain on this hidden connection.
Remember that classic experiment where an electric current makes a compass needle move? That was a huge clue.
It was. Suddenly, there's undeniable proof that moving electric charges create magnetic fields. And so naturally, the next question pops up. If electricity can create magnetism, can magnetism, in turn, create electricity?
And the answer, as we now know, is a resounding yes. That's the essence of electromagnetic induction, the story of this discovery. Well, it's got its own share of drama, with two brilliant minds working independently, Michael Faraday in England and Joseph Henry, right here in the U.S. back in the 1830s.
Two scientific giants. And both of them, around the same time, showed that a changing magnetic field could induce an electric current in a closed loop of wire. It sounds simple, almost too simple.
It does, doesn't it? But that simple observation had monumental consequences.
Oh, absolutely. But it wasn't always obvious. There's that famous anecdote about Faraday, right? He's demonstrating this phenomenon, showing how a moving magnet near a coil of wire can generate a current, and someone asks him, what good is it? Like, what's the practical use?
And Faraday, with his incredible vision, he replies, what is the use of a newborn baby? Brilliantly put. He saw the potential even when others couldn't.
He knew it was the birth of something huge, something that would change the world.
And he was absolutely right. Imagine our world without electricity as we know it. No lights, no trains, no phones, no computers.
That's a world I don't even want to imagine. We take electricity for granted now. But it's all thanks to that fundamental discovery, that connection between magnetism and electricity. Faraday and Henry. Their work directly led to the invention of generators and transformers.
The cornerstones of our modern electrical grid.
So let's dive a bit deeper into the experiments that revealed this incredible phenomenon. Our sources describe several key experiments, and they really lay the foundation for understanding electromagnetic induction.
Excellent. It's always good to start with the basics, the foundations.
Exactly. So, experiment 6.1, the setup is quite elegant. Imagine a coil of wire, we can call it C1, connected to a galvanometer. A galvanometer, just as a reminder, is a device that can detect small currents.
Very sensitive, those galvanometers.
Indeed. Now, you take a simple bar magnet and move its north pole towards this coil, and guess what? The needle on the galvanometer, it jumps.
It deflects, right, showing that an electric current has been induced in the coil. But here's the crucial thing. The current flows only while the magnet is moving. Stop the magnet, the current disappears. It's all about the change.
That's a really important point. It's not just the presence of the magnetic field, but the fact that it's changing that induces the current. And the experiment didn't start there. They pulled the magnet away and saw another deflection, this time in the opposite direction.
Right, meaning the induced current reverse direction. And if you use the south pole of the magnet instead, more reverse deflections, it all points to the importance of the direction of the magnetic field and how it's changing.
Fascinating, isn't it? And there's more. The faster you move the magnet, the larger the deflection, meaning a stronger current. So speed plays a role too.
It does. It all boils down to the rate at which the magnetic field is changing near the coil.
Okay, ready for experiment 6.2. This time, instead of a permanent magnet, we're using another coil, C2, connected to a battery to create a steady current and therefore a steady magnetic field.
So we've replaced the permanent magnet with an electromagnet, essentially.
Exactly. Now, what happens if you move the second coil, C2, towards our first coil, C1? Well, just like before, you get a deflection on the galvanometer connected to C1, meaning there's an induced current. And as you pull C2 away, the deflection reverses.
And just like with the magnet, if you hold one coil still and move the other, you still get the induced current. It's the relative motion that matters, whether it's the magnet or the coil that's moving. As long as the magnetic field experienced by the first coil is changing, you get that induced current.
Okay, so far so good. But now comes experiment 6.3, and this one really takes things to a whole new level. In this setup, both coils, C1 and C2, are stationary. C1's still connected to the galvanometer, but C2's circuit now includes a switch or a tacting key labeled K.
All right, let's see what this new twist brings.
So you press the key, closing the circuit for C2, and something interesting happens. The galvanometer in C1 shows a momentary deflection. Just a quick blip and then back to zero, even though the current in C2 is still flowing. So we've got a constant current, a steady magnetic field, but only a momentary induced current. What's going on there?
It all comes down to change. Again, when you press the key, the current in C2 suddenly jumps from 0 to some value. That creates a rapid change in the magnetic field.
Right, a sudden surge. But then, as the current in C2 settles down to a steady value, the magnetic field also becomes steady. No more change, no more induced currents.
When you release the key, breaking the circuit for C2.
Another momentary deflection, but in the opposite direction. Because now the current in C2 rapidly drops to 0, again causing a change in the magnetic field. There's one more crucial detail. If you insert an iron rod through the center of both coils, those momentary deflections get much stronger.
So it amplifies the effect. The iron core intensifies the magnetic field, making those changes even more pronounced.
It really highlights the key takeaway from this experiment. It's not simply motion that matters, but a changing magnetic field. That change can be caused by motion, but it doesn't have to be.
It's the dynamic nature of the field is the heart of electromagnetic induction.
This brings us to a key concept, magnetic flux. It's often represented by the symbol VB.
Think of it as a measure of how much magnetic field is passing through a given area. It's analogous to electric flux, which measures electric field passing through an area.
Right, so if you have a uniform magnetic field, B, passing through a flat surface of area A, the magnetic flux is simply the dot product of B and A, BA cosine, where is the angle between the magnetic field and the normal to the surface.
Precisely. And in more complex scenarios where the field's not uniform or the surface isn't flat, You'd break things down into tiny areas and sum up the contributions. But the basic idea is the same. It's a measure of the total magnetic field passing through a surface.
The SI unit is the Weber, or Belubab, which is equivalent to a Tesla meter squared.
A nice, compact unit.
It is. Now, with the concept of magnetic flux in hand, we can finally talk about the big one, Faraday's law of induction. This law, based on all those brilliant experiments, states that an electromotive force, or M thing, is induced in a coil whenever the magnetic flux through that coil changes over time.
It's the mathematical embodiment of this connection between changing magnetism and electricity.
For a single loop of wire, the law can be written as AAT equals negative dB.
Ah, that negative sign. It's not just there for decoration.
Exactly. It's a hint at something deeper. Lenz law, which we'll get to in a bit. But first, just focusing on Faraday's law, it tells us that the induced EMF, that's essentially the voltage that can drive a current. It's directly proportional to how fast the magnetic flux is changing. And if you have a coil with N turns of wire, the total F becomes A equals negative N times dB/dt.
More turns, more induced voltage.
Precisely. And if we go back to those experiments, we can see Faraday's law in action. In experiments 6.1 and 6.2, moving the magnet, or the current-carrying coil, that changed the magnetic flux through the other coil, leading to that induced current we saw.
And experiment 6.3, switching the current on or off in that second coil. That also changed the magnetic flux through the first coil, resulting in those momentary blips of current.
It all fits perfectly. And remember how there are different ways to change the magnetic flux. We can vary the strength of the field, the area of the loop, or the angle between them. Any of those will induce an F according to Faraday's law.
The possibilities are endless.
Now, about that negative sign in Faraday's law, that brings us to Lenz's law, named after the physicist Heinrich Lenz. This law states that the direction of the induced EMF will always be such that it opposes the change in magnetic flux that produced it.
It's like the system is trying to resist the change to maintain the status quo. A bit of inertia, but for magnetic fields.
I like that analogy. So let's go back to experiment 6.1 with the moving magnet. When you move the north pole towards the coil, the flux through the coil increases.
Right. More field lines passing through it.
According to Lenz's law, the induced current in the coil will create its own magnetic field, and that field will try to oppose the increase in flux. So the coil effectively becomes like a magnet with its north pole facing the approaching magnet.
Repelling it, trying to push it back.
Yeah.
And if you pull the magnet away, the flux through the coil decreases.
In that case, the induced current creates a field that tries to oppose the decrease. The coil acts like a magnet, this time with its south pole facing the receding magnet, trying to pull it back in.
Always resisting the change.
And this opposition, it's not some random quirk. It's deeply connected to the principle of conservation of energy. If the induced current aided the change in flux, well, you'd have this runaway effect. A small change would lead to more current, which would lead to a bigger change, and so on, in an endless cycle of increasing energy, violating one of the most fundamental laws of physics.
We can't have that. Perpetual motion machines. They just don't exist in our universe.
Exactly. The fact that the induced current opposes the change, that means you have to put in work to move the magnet against that resistance, that work you do. That's where the energy comes from. It gets converted into electrical energy and then dissipated as heat in the coil due to its resistance.
It all balances out beautifully. And even in an open circuit where no current can actually flow, you still get an induced EMF across the open ends. It's always there, ready to oppose any change in flux.
Our source includes example 6.4, which shows Lenz's law with loops of different shapes moving in and out of a magnetic field. It's a great way to visualize how the direction of the induced current always works to counteract those changes in flux, no matter how strange the loop might look.
And then example 6.5, it really makes you think. It highlights that just having a strong stationary magnet, that's not enough to induce a current. There has to be a change in flux. And it also points out that changing electric flux, that doesn't directly induce a current. That's a different phenomenon altogether, governed by a different set of laws.
And that example also looks at how the induced F behaves as a loop moves out of a uniform field. For a rectangular loop, the EMF stays constant, but for a circular loop, it changes, all because of the way the area within the field changes over time.
It's fascinating how those subtle differences in geometry can have such significant effects.
It really is. And to wrap up that example, it even explores how to figure out the polarity of a capacitor that's being charged by an induced EMF based on the direction of the changing magnetic flux.
Really putting those concepts to the test.
Okay, let's shift gears a bit and talk about motional electromotive force. This is a specific case of electromagnetic induction where the EMF is created because a conductor is physically moving through a magnetic field. Imagine a straight conductor, let's call it PQ, moving with a velocity v in a uniform magnetic field B. The field is perpendicular to both the motion and the conductor.
Right, I'm picturing it.
Now, let's complete this picture by adding a rectangular loop, PQRS, where PQ is our moving conductor. As PQ moves, the area of this loop changes, right?
Absolutely.
Yeah.
It gets bigger or smaller, depending on which way PQ moves.
And since there's a magnetic field passing through the loop, that means the magnetic flux is also changing. So if we apply Faraday's law to this scenario, we find that an EMF is induced in the loop, and it's given by A equals BL. L is the length of the conductor PQ, and V is its speed.
A nice simple formula.
Yeah.
And what's really cool is that you can arrive at that same result
Mhm.
by considering the forces acting on the charges inside the moving conductor.
Right. It's like two different perspectives converging on the same truth. When that conductor moves through the magnetic field, the charges within it experience a magnetic force.
The Lorentz Force.
Exactly. And this force causes the charges to separate, creating an electric field and therefore an F within the conductor. It's the same BLV we got from Faraday's law.
Beautiful. It highlights the interconnectedness of these different concepts.
Mhm.
And it's worth noting that motional EMF, it's specifically about a conductor moving in a static field. Faraday's law is more general, covering situations where a stationary conductor experiences a changing field. In fact, a time-varying magnetic field. It actually creates an electric field. That was one of Maxwell's brilliant insights.
It's all connected. Our source provides some great examples to illustrate this concept of motional EMF. Example 6.6 talks about a rotating rod in a magnetic field. The rotation induces an F between the center and the rim. What's neat is that you can calculate this F in two ways, using the idea of motional EMF, or by applying Faraday's law to the changing area swept by the rod.
Two different approaches, same result.
And then example 6.7. This one imagines a rotating wheel with metal spokes placed in the Earth's magnetic field. The rotation creates an F between the axle and the rim. But here's the interesting part. The number of spokes doesn't matter. The EMFs induced in each spoke are essentially connected in parallel, so the total EMF is the same.
Those examples really help to bring those abstract ideas down to earth.
All right, on to our final concept, inductance. In essence, it's a measure of how well a coil, or any circuit, can induce an EMF either within itself or in another nearby circuit when the current flowing through it changes.
It's all about how changes in current translate to changes in magnetic flux. It's like a measure of the circuit's magnetic responsiveness.
I like that. We can define inductance as the constant of proportionality that relates the magnetic flux linkage, that's a total flux passing through all the turns of a coil, to the current.
So if you have n turns and a flux of BVAB through each turn, the total linkage is NA, and that's proportional to the current. The constant proportionality is what we call inductance.
Now, there are two main types of inductance: mutual inductance and self-inductance.
Mutual inductance is all about the interaction between two separate coils.
Right. So imagine two coils close to each other. Current I2 flowing through the second coil creates a magnetic field, and some of that field passes through the first coil, creating a flux A1 in that coil. The total linkage, N11, in the first coil is proportional to the current I2 in the second coil, and the constant of proportionality is, you guessed it, the mutual inductance, M12.
And you can do the same thing in reverse. Current I1 in the first coil induces a flux A2 in the second coil, and you get a mutual inductance M21. The amazing thing is, for many arrangements, those two values are equal.
That's right. We just call it M, the mutual inductance between the coils. And this M, it depends on the shapes and positions of the coils, how far apart they are, their relative orientation, and the material surrounding them.
It's all about their magnetic interaction.
Example 6.8 in our source, it dives into this. It calculates the mutual inductance between two concentric coils where one's much smaller than the other.
A classic scenario. And remember, we can link mutual inductance back to Faraday's law. If the current I2 in the second coil changes at a rate of di2 dt, it will induce an F in the first coil given by A1 equals negative m times di2 dt.
It all ties together beautifully.
Indeed. Now, let's talk about self-inductance. It's denoted by L.
This one's all about what happens within a single coil itself.
It's like a coil having a conversation with itself.
Haha, I like that. So when the current in a coil changes, the magnetic flux that the coil itself produces also changes, right?
Of course. A changing current means a changing magnetic field, which means a changing flux.
And according to Faraday's law, that change in flux induces an EMP within the coil itself. It's called self-induction. And guess what? The flux linkage NB of the coil is proportional to the current I flowing through it.
And the constant of proportionality is?
You know it. It's the self-inductance, L. So NB equals Li. And just like with mutual inductance, we can relate it to the induced EMF. If the current changes at a rate of dA, the self-induced EMF, sometimes called the back EMF, is A equals negative L times dAt, that negative sign.
It means the induced EMF always tries to oppose the change in current, like an electrical inertia.
It's like the coil is trying to resist any change in its current flow. And our source shows how to calculate this self-inductance for a long solenoid. It depends on the length, the area, and the material inside the solenoid.
And just as a moving object has kinetic energy, an inductor with a current flowing through it, it stores energy in its magnetic field.
The formula is W equals 1/2 Li squared.
A nice parallel to kinetic energy, which is 1/2 meter V squared.
And example 6.9. It explores the magnetic energy stored in a solenoid and compares its energy density, the energy per unit volume, to the electrostatic energy density in a capacitor.
A fascinating comparison. It turns out both are proportional to the square of their respective field strengths. Nice little symmetry there.
And finally, we get to one of the most important applications of electromagnetic induction, the AC generator.
The heart of our electrical grid.
It converts mechanical energy into electrical energy, all thanks to those principles we've been discussing. It was a game changer, really, especially with the contributions of people like Nikola Tesla.
A true visionary.
The idea behind an AC generator is quite simple. A coil of wire is rotated within a magnetic field. As it spins, the magnetic flux through the coil changes constantly because the coil's orientation relative to the field is always changing.
And according to Faraday's law, that changing flux induces an F in the coil.
Exactly. The basic components are the coil, called the armature, which is mounted on a rotating shaft, the rotor. Then you need a strong magnetic field, usually provided by permanent magnets or electromagnets. And of course, something to provide the mechanical energy to spin the rotor like a turbine. And finally, slip rings and brushes to connect the rotating coil to the external circuit.
All working together to generate that precious electricity.
Now, as the coil rotates at a constant speed, omega, the induced EMF, varies sinusoidally with time. It's given by A equals MBA omega times sine of omega t. N is the number of turns, B is the field strength, A is the area of the coil, and omega is the angular speed. And the maximum EMF, that's simply A equals NBA omega.
A nice compact formula.
And because the induced EMF is sinusoidal, it means the direction of the current flips back and forth, hence the name alternating current, or AC, the frequency, N, of that AC current. It's directly related to the angular speed, omega. Omega equals 2 pnm.
Makes sense. The faster it spins, the higher the frequency.
Whether it's a hydroelectric dam using falling water, or a thermal power plant burning fossil fuels, or using nuclear power to generate steam, they all rely on this principle. And the standard frequency varies around the world. Here, it's 60 hertz, but in many other places, it's 50 hertz.
Interesting. A bit of global variation.
Our source has a nice little example, 6.10. It describes someone pedaling a bicycle, which is connected to a coil in a magnetic field. It then calculates the maximum voltage they generate.
A fun way to connect it to something we can all visualize.
It is. So to wrap things up, let's take a moment to appreciate what we've learned. We've explored this incredible connection between electricity and magnetism through the lens of electromagnetic induction, a connection first revealed by Faraday and Henry. We've seen how Faraday's law captures that relationship mathematically, how Lenz's law tells us about the direction of the induced EMF, and how those ideas of magnetic flux and inductance, they're all intertwined in this beautiful dance of electromagnetism.
And most importantly, we've seen how these seemingly abstract discoveries have led to technologies that have completely transformed our world. Generators, transformers, and everything they power. It's all thanks to electromagnetic induction.
It really makes you think how these fundamental insights can have such a profound impact on the world we live in. And it's not over yet.
That's right. We've talked about how moving charges create magnetic fields, and how changing magnetic fields create electric fields. What if we could go even deeper into this relationship? What other possibilities are out there just waiting to be discovered? Imagine the technologies we might unlock with an even more profound understanding of these fundamental forces.
It's a thought that's both exciting and humbling.
It is. The quest to understand electromagnetism. It's a journey that's far from over, and who knows what wonders await us along the way.
Well said. And on that note, we'll leave you with that thought. Thanks for joining us for another deep dive.
It's been a pleasure.
Until next time.
See you then.
Chapter 7. Alternating Current.
Welcome back, everyone, to the deep dive. Today, we are going to try to understand this thing called alternating current.
AC.
AC. So, I mean, I know that it powers pretty much every, home and office.
Right.
You know, everything that I plug in. I mean, I guess pretty much everything runs on AC.
Pretty much everything. I mean, there are some things that are DC, but AC is really the standard.
Okay, so I guess the question that comes to mind is, why? Why AC? Why is this the dominant form of, electrical power that we use?
So the biggest reason is that AC can be transformed in terms of its voltage
Okay.
very easily using a device called a transformer.
Oh, okay.
So you can step up the voltage or step down the voltage using a transformer.
Okay.
And why that's important is that you can transmit electricity over long distances. So you can generate electricity, let's say, at a power plant,
Right.
a dam, or a nuclear power plant, or even a solar farm. You can generate it, step up the voltage, and then transmit it over long distances with minimal losses. And then when it gets to your house, you step it back down to a voltage that's safe for you to use.
Right.
So that's one of the biggest reasons why AC is so prevalent.
So today we're going to do a deep dive into the fundamentals of AC circuits.
Absolutely.
So starting with kind of simple components like resistors, inductors, capacitors,
Right.
and then kind of working our way up to understanding more complex behaviors, like how does a radio work, like how does that tuning dial actually tune into a specific frequency.
That's a good point. Yeah.
That's AC circuits.
Yeah.
So before we kind of get into the nitty-gritty, there are a couple people that we should acknowledge that really were the pioneers of AC, Nikola Tesla and George Westinghouse.
Right.
So Tesla was an inventor, engineer, physicist. I mean, he was way ahead of his time.
Absolutely visionary.
Visionary, yeah. He's credited with inventing the rotating magnetic field, which is basically the fundamental principle behind AC machinery.
Right. That's the core concept that makes motors spin, generators work. Yeah.
Also, the induction motor. He developed polyphase AC systems, which I think we'll probably get into later on in our discussion. And then, the famous Tesla coil, which I think everybody's, probably at least seen in a movie or something like that.
Right. Yeah. Yeah. It captures the imagination.
Yeah, for sure. And then George Westinghouse, he was more of kind of like the business guy.
Right. The entrepreneur, the champion.
The champion of AC as opposed to DC.
Right.
So he was a big proponent of using AC for wide-scale power distribution, and they kind of teamed up and really brought AC to the masses.
Yeah, a great partnership. Tesla with the vision and Westinghouse with the means to actually make it happen, to build it out.
Exactly. Okay, so let's talk about AC voltage. Applied to a resistor first.
Okay.
So I mean, a resistor is a pretty basic circuit component.
It is, yeah.
And we know, like I said, that AC is basically it's kind of it fluctuates.
It alternates, yeah.
It alternates,
yeah.
So it's going positive, negative, positive, negative.
Right.
So it's not like a steady DC voltage.
Right. DC would just be a flat line. AC is, it's going up and down like a wave.
So let's talk about how do we actually represent AC voltage, mathematically?
So we use a sinusoidal function to represent AC voltage.
Okay.
So the equation is V of t equals Vm sine of omega t.
Good.
So V of t is the voltage at any given time. T.
Okay.
Vm is the amplitude of the voltage, which is the maximum value.
Okay.
Omega is the angular frequency.
Okay.
And t, of course, is time.
And what are the units for those? So the amplitude is volts.
Amplitude would be in volts.
Okay.
Time would be in seconds. And angular frequency would be in radians per second.
Okay.
And that's because we're talking about something that's oscillating. It's going back and forth. And so radians are a good way to measure an angle, essentially.
Right.
So you can think of omega t as an angle.
Okay.
That's changing over time.
Okay. So what happens when we apply this AC voltage to a resistor?
So when we apply AC voltage to a resistor, the current through the resistor is also sinusoidal.
Okay.
And it follows Ohm's law, which is epsilon of t equals IR.
Okay.
So epsilon of t is the voltage at any given time. I is the current at any given time, and R is the resistance.
Okay.
So since the resistance is constant, the current is going to be proportional to the voltage.
Okay.
So if the voltage is sinusoidal, the current is also going to be sinusoidal.
So it's also going to kind of oscillate back and forth at the same frequency.
Exactly, yeah.
Okay.
So it's going up and down in sync with the voltage.
Okay. So mathematically,
Yeah.
how do we represent that?
So the equation for the current is I of t equals Im sine of omega t. So I of t is the current at any given time.
Okay.
Im is the amplitude of the current, which is the maximum value.
Okay.
And omega and t are the same as before.
And what's the relationship between the voltage amplitude and the current amplitude?
So the relationship is Im equals Vm divided by R.
Okay.
So that comes from Ohm's law.
Got it.
Epsilon of t equals IR.
Okay. So that's kind of interesting. So the amplitude of the current is determined by the amplitude of the voltage divided by the resistance.
Right. So the higher the voltage, the higher the current.
Right.
And the higher the resistance, the lower the current.
Okay. And we say that the voltage and current are in phase in this circuit.
Right, exactly.
So what does that mean?
So in phase means that the voltage and current reach their maximum values, their minimum values, and their zero values at the same time.
Okay.
So they're perfectly synchronized.
It's like they're like dancing together.
Exactly.
Okay. So now let's talk about power.
Okay.
So we know that AC current is oscillating back and forth.
Right.
So I mean, does that mean that the average current is zero?
That's correct, yes. The average current over a full cycle is zero because it's spending half its time going one way, half its time going the other way.
Okay. So, but things still work. Like, I turn on a light bulb and it lights up.
Right, exactly.
So how is that possible?
So the power dissipation in a resistor is given by I squared R.
Okay.
So even though the average current is zero, the average of the current squared is not zero.
Okay, so it's always a positive value.
Exactly, yeah, because you're squaring it. So even if the current is negative, the square of a negative number is positive.
Right.
So the power dissipation is always positive.
So let's talk about, like, how do we actually calculate the average power?
Okay, so the instantaneous power P is given by I squared R, which is the same as I spin squared R sun squared omega t. And then the average power, which we denote as P with kind of brackets around it, is 1/2 Im squared R.
Okay, and so that's the average power that's being dissipated by the resistor.
Correct, yeah.
Okay. And that's also the power that's being delivered by the AC source, right?
Exactly.
Yeah. Now we talk about something called RMS current, right?
Right. Root means square current, RMS.
Okay, and so what is that?
So the RMS current is the equivalent DC current that would produce the same average power loss.
Okay.
So it's a way to kind of compare AC and DC circuits.
Okay.
And the equation for the RMS current is IRMS equals IM divided by the square root of 2.
Okay.
Which is approximately 0.707 IM.
Okay. So basically RMS values give us like a way to use like familiar formulas like power equals I squared R, but in an AC circuit.
Exactly.
Okay. And then similarly we define RMS voltage, right?
Right.
And that's just VM divided by square root of 2.
Correct. Yeah.
Okay. So that's pretty much it for resistors, right?
Yeah, pretty much.
Okay. So now let's move on to something a little bit more complicated.
Okay.
Let's talk about inductors.
Okay, so inductors are interesting because they oppose changes in current.
Okay.
So they don't like it when the current tries to change too quickly.
So like if you try to increase the current, it's going to like fight back.
Exactly, yeah. It's going to resist that change.
Okay.
And vice versa. If you try to decrease the current, it's going to try to keep it going.
Oh, okay.
And the way it does that is by creating a magnetic field.
Okay.
So when current flows through an inductor, it creates a magnetic field around the inductor. And then when the current tries to change, that magnetic field induces a voltage in the inductor that opposes that change.
Okay.
So it's kind of like a flywheel.
Oh, okay.
If you try to spin a flywheel up,
Right.
it takes a while for it to get going.
Right.
And then once it's going, it's hard to stop it.
Right.
So it's kind of the same idea with an inductor.
Okay. So how does this like play out in an AC circuit?
So in an AC circuit, the voltage across the inductor is given by V equals LdI dt. So L is the inductance of the inductor. E dt is the rate of change of current.
Okay.
So if the current is changing sinusoidally, the voltage across the inductor is also going to be sinusoidal, but it's going to be shifted in phase.
Okay.
So the current is going to lag the voltage by 90 degrees.
So the current is always kind of behind the voltage.
Exactly, yeah.
Okay.
It's like the current is always trying to catch up to the voltage.
Okay, and how do we represent that mathematically?
So the equation for the current in an inductor is I of t equals negative Vm over omega L cosine of omega t.
Okay.
Which can also be written as I of t equals Vm over omega L sine of omega t minus pi over 2.
Okay, so the pi over 2, that's the 90 degrees.
Exactly,
Okay.
yeah. So that's what's causing that phase shift.
Okay, and then we talk about inductive reactance, right? And what is that?
So inductive reactance is the opposition to current flow by an inductor.
Okay.
And it's given by XL equals omega L.
Okay.
So omega is the angular frequency, L is the inductance.
Okay, and the unit is ohms.
Correct. Yeah.
Okay. So basically the inductive reactance determines how much the inductor is going to resist the flow of current.
Right, exactly.
Okay. And so if we have like a higher frequency AC voltage, then that means that the inductive reactance is going to be higher.
Right, exactly.
Okay. And so let's talk about power in an inductor.
Okay, so the average power supplied to a pure inductor over a complete cycle is 0.
Okay. So even though current is flowing.
Right.
Okay.
So the energy is actually stored in the magnetic field of the inductor during one part of the cycle, and then it's released back to the circuit during another part of the cycle.
So it's not actually being, like, dissipated.
Correct, yeah. It's just being stored and released.
Okay. And so that's why the average power is 0.
Exactly, yeah.
So now let's move on to capacitors.
Okay, so capacitors are kind of the opposite of inductors.
Okay.
They oppose changes in voltage.
Okay.
So if you try to increase the voltage across a capacitor, it's going to resist that change.
Okay.
And vice versa, if you try to decrease the voltage, it's going to try to keep it going.
Okay.
And the way it does that is by storing charge.
Okay.
So a capacitor is basically two conductive plates separated by an insulator. And when you apply a voltage across the capacitor, charge builds up on the plates.
Okay.
And then when you try to change the voltage, that charge creates a current that opposes that change.
Okay. And so how does this like play out in an AC circuit?
So in an AC circuit, the current through the capacitor is given by I equals C dV dt.
Okay.
So C is the capacitance of the capacitor. dV dt is the rate of change of voltage.
Okay.
And so if the voltage is changing sinusoidally...
Right. The current through the capacitor is also going to be sinusoidal, but it's going to be shifted in phase.
Okay.
So the current is going to lead the voltage by 90 degrees.
Oh, so it's the opposite of the inductor.
Exactly, yeah.
Okay.
So it's like the current is always ahead of the voltage.
So it's like instead of like playing catch up, it's like, you know, it's like, I don't know, it's like...
It's like the leader.
It's the leader.
Yeah.
Okay, yes. It's like it knows what's going to happen before the voltage does.
Right.
Okay. And then how do we represent that mathematically?
So the equation for the current in a capacitor is I of t equals omega c Vm cosine omega t.
Okay.
Which can also be written as I of t equals Vm over 1 over omega c sine of omega t plus pi over 2.
Okay.
So again, the pi over 2 is what's causing that 90-degree phase shift.
Okay. And then we talk about capacitive reactance.
Yeah.
So what is that?
So capacitive reactance is the opposition to current flow by a capacitor.
And it's given by XC equals 1 over omega C.
Okay.
So omega is the angular frequency, C is the capacitance.
Okay. And the unit is, again, ohms.
Correct.
Yeah.
Okay.
And so the capacitive reactance determines how much the capacitor is going to resist the flow of current.
Right. Exactly.
Okay. And so if we have a higher frequency AC voltage, then the capacitive reactance is actually going to be lower.
Right. Exactly.
So it's the opposite of the inductor.
Right. Exactly.
Okay. Now let's talk about power in a capacitor.
Okay, so just like with the inductor, the average power supplied to a pure capacitor over a complete cycle is 0.
Okay.
So in this case, the energy is stored in the electric field of the capacitor during one part of a cycle, and then it's released back to the circuit during another part of the cycle.
So again, no net dissipation of energy.
Correct.
Okay.
Mm-hmm.
So I think we've kind of covered resistors, inductors, and capacitors individually.
Yeah.
So what happens when we like combine them all together?
Yeah. Okay. So when we combine them all together, we get what's called an LCR circuit.
LCR.
Yeah, for inductor, capacitor, resistor.
Okay.
And things get really interesting there because now you've got all these different phase shifts going on.
Right.
So the voltage and current are no longer necessarily going to be in phase with each other.
Okay. So it's not as simple as like, you know, the current is always lagging the voltage, or the current is always leading the voltage.
Right.
Okay.
It can be any of those,
Okay.
or it can be somewhere in between.
Right. Okay.
Depending on the values of the components and the frequency of the AC source.
So how do we like analyze an LCR circuit?
So to analyze an LCR circuit, we use something called a phasor diagram,
Okay.
which is a way to visually represent the phase relationships between the voltage and the current.
Okay. So it's like a graph, basically.
Kind of, yeah.
Right.
So you draw vectors that represent the voltage and the current, and the angle between those vectors represents the phase difference between the voltage and the current.
Okay.
So for example, for a resistor, the voltage and current are in phase, so the vectors would be pointing in the same direction.
Right.
For an inductor, the current lags the voltage by 90 degrees.
Right.
So the current vector would be 90 degrees behind the voltage vector.
Okay.
And for a capacitor, the current leads the voltage by 90 degrees.
Right.
So the current vector would be 90 degrees ahead of the voltage vector.
Okay. So you can actually like draw these things out.
Right.
And you can see the relationships between the different voltages and the current.
Exactly. Yeah.
Okay. And then we talk about impedance in an LCR circuit.
Right.
And so what is impedance?
So impedance is the total opposition to current flow in an AC circuit.
Okay.
And it's given by Z equals the square root of R squared plus XL minus XT squared. So R is the resistance, XL is the inductive reactance, and XC is the capacitive reactance.
Okay. And again, the unit is ohms.
Correct.
Okay. So impedance is kind of like, it's like a combination of resistance, inductive reactance, and capacitive reactance.
Okay.
Yes.
It takes into account all of those things.
Okay. And so the impedance determines how much current is going to flow in the circuit.
Right.
For a given voltage.
Exactly.
Okay. And then we define something called the phase angle, right?
Right.
And what's the phase angle?
So the phase angle is the angle between the voltage and the current phasors.
Okay.
And it's given by tan phi equals XL minus XCL over R.
Okay.
So phi is the phase angle.
Okay.
And so a positive phase angle means that the current lags the voltage.
Okay.
A negative phase angle means that the current leads the voltage.
Okay.
And a zero phase angle means that the voltage and current are in phase.
Okay. So that's kind of like a summary of all the different phase relationships that we've been talking about.
Right.
Okay. Now let's talk about something really cool.
Huh?
Resonance.
Yeah, resonance is a really interesting phenomenon.
Okay.
It occurs when the inductive reactance and the capacitive reactance are equal.
Okay, so XL equals XC.
Exactly.
Okay.
And when that happens, the impedance of the circuit is minimized.
Okay.
And the current through the circuit is maximized.
Oh, okay.
And the frequency at which this occurs is called the resonant frequency.
Okay, and how do we calculate that?
So the resonant frequency is given by S0 equals 1 over 2 pi times the square root of LC.
Okay.
So L is the inductance, C is the capacitance.
All right.
And so at the resonant frequency,
Mm-hmm.
the circuit is basically oscillating at its natural frequency.
Oh, okay.
And so it's very easy to transfer energy into the circuit at that frequency.
Okay.
So it's kind of like pushing a swing.
Oh.
You know, if you push a swing at the right frequency,
Right.
you can get it to swing really high.
Right, with very little effort.
Exactly.
Okay.
And it's the same idea with resonance.
Okay. So, what are some examples of where resonance is used?
So resonance is used in a lot of different applications. One example is radio tuning.
Okay.
So in a radio, you have an LCR circuit, and you can adjust the capacitance of the circuit.
Okay.
And by adjusting the capacitance, you change the resonant frequency.
Okay.
And so when you tune your radio to a particular station, you're basically adjusting the capacitance of the circuit so that its resonant frequency matches the frequency of the radio station.
Okay, so it's only picking up that one frequency.
Right, exactly.
Okay.
And then another example is musical instruments.
Okay.
So a lot of musical instruments rely on resonance to produce sound.
Okay.
So, for example, a guitar string. When you pluck a guitar string, it vibrates at its natural frequency.
Right.
And that vibration is amplified by the body of the guitar.
Okay.
Which is basically a resonant cavity.
Okay, so it's like the body of the guitar is designed to resonate at specific frequencies.
Exactly.
Right.
Yeah.
Okay. So I guess that kind of covers LCR circuits and resonance.
Yeah, pretty much.
Okay. So now let's talk about power in an AC circuit.
Okay.
And specifically the power factor.
Okay, so the power factor is a measure of how effectively power is being used in an AC circuit.
Okay.
And it's given by cosine phi.
Okay.
So phi is the phase angle.
Right.
And so if the phase angle is 0, which means that the voltage and current are in phase, then the power factor is 1.
Okay.
And that means that all of the power that's being supplied to the circuit is being used.
Okay, so that's the ideal situation.
Right, exactly.
Okay.
But if the phase angle is not 0, then the power factor is less than 1.
Okay.
And that means that some of the power that's being supplied to the circuit is not being used.
Okay, and where does the power go?
So that power is basically being stored and released by the reactive components in the circuit. Okay. The inductors and the capacitors.
Right.
So it's not actually being dissipated. It's just kind of sloshing back and forth.
Okay.
And that can be a problem because it can lead to higher currents in the circuit.
Okay.
Which can lead to higher losses.
Okay, so a low power factor is a bad thing.
Generally speaking, yes.
Okay.
Yeah.
So how do we improve the power factor?
So one way to improve the power factor is to add capacitors to the circuit.
Okay.
So if you have a circuit that has a lot of inductive load, like a lot of motors, then the current is going to lag the voltage.
Right.
And so the power factor is going to be low.
Okay.
But if you add capacitors to the circuit, then that will help to bring the current back into phase with the voltage.
Okay.
And so that will improve the power factor.
Okay. So capacitors kind of counteract the effect of inductors.
Right. Exactly.
Okay. Now let's talk about the last thing on our list, which is transformers.
Okay. So transformers are devices that are used to change the voltage of AC electricity.
Okay.
And they work by using the principle of electromagnetic induction.
Okay.
So basically you have two coils of wire that are wrapped around a common core.
Okay.
And when you apply an AC voltage to one of the coils, it creates a changing magnetic field.
Okay.
And that changing magnetic field induces a voltage in the other coil.
Okay.
And the ratio of the voltages in the two coils.
Chapter 8. Electromagnetic Waves.
All right, so have you ever, taken off a sweater and gotten zapped by static? Or, look at a compass and been like, whoa, how does that even work?
Yeah, or just, seen anything at all because of, light.
Right, light, it's everywhere. But here's the thing. What if I told you those are, all connected, deeply connected?
It sounds crazy, but it's true. It all comes down to this thing called electromagnetic waves.
And that's what we're diving into today, right? A bunch of you asked for, a way simpler explanation of EM waves.
And we've got some awesome sources that break it all down from, the very basics to all the different types of EM waves out there.
Yeah, and we're going to try to make it, click without getting too lost in the, super technical stuff. So to kick things off, we have to talk about this guy, James Clerk Maxwell.
Yeah, Maxwell. This dude was, a total genius. He basically figured out the whole electricity and magnetism thing.
Before him, people thought they were totally separate forces, right?
Exactly. But Maxwell is like, nope, they're two sides of the same coin. And the key was his realization that, get this, a changing electric field actually creates a magnetic field.
Whoa. Okay. So how did he even figure that out?
Well, it all started with, a little mystery. Back then, scientists knew that if you have electricity flowing through a wire, you get a magnetic field around it, like an invisible force field.
Okay, yeah. I kind of remember that from, high school physics.
Right. But then Maxwell looked at this thing called a capacitor. Basically, it's have two metal plates that store electrical energy. When you're charging it up, you have electricity flowing in one side and out the other through wires, right?
So far, so good.
But here's the weird part. Between those plates, there's no actual flow of charge, ideally. It's just empty space or maybe some insulator.
Interesting.
So if you applied the old rules of magnetism, you'd think, okay, no current flowing between the plates, so there shouldn't be any magnetic field there, right?
Makes sense, I guess.
But the problem was, there totally was a magnetic field. Like, it didn't just magically disappear in that space between the plates.
Huh. So something else had to be creating that magnetic field.
Right, exactly. And Maxwell's like, wait a minute, what if the changing electric field itself is acting like a current? Because as the capacitor charges up, the electric field between the plates is getting stronger, right? It's changing.
Oh, I see. So he's saying that even though there are no actual charges moving between the plates, the changing electric field itself is what's creating the magnetic field.
Bingo. He called this the displacement current, which, yeah, sounds kind of fancy. But think of it like this. The changing electric field is kind of like pushing or displacing the electric field lines around it. And that push creates the same effect as a regular electric current in terms of generating a magnetic field.
I get it. So it's like a phantom current. It's not a flow of charges, but it acts like one because the electric field itself is changing.
And get this. He even figured out how to measure this displacement current. Basically, it depends on how quickly that electric field is changing. The faster the change, the stronger the displacement current and the magnetic field it creates.
So he basically like patched up the whole theory of electromagnetism, right?
Totally. And it wasn't just a patch, it was like super elegant. It brought this beautiful symmetry to the whole thing. Because before Maxwell, we knew that a changing magnetic field could create an electric field.
Right, like how generators work, right?
Exactly. But Maxwell showed that the reverse is also true. A changing electric field creates a magnetic field. It's like they're in this constant dance, each influencing the other.
That's pretty mind-blowing.
And it gets even weirder. This displacement current isn't just some theoretical thing. It exists even in totally empty space, where there are literally no charged particles at all. It's purely a consequence of the electric field changing over time.
Wow. Okay, so if changing electric fields make magnetic fields, and changing magnetic fields make electric fields, what happens when, like, both are changing at the same time?
Well, that's where things get really interesting. Maxwell's equations predicted that under the right conditions, these changing fields can become self-sustaining and actually travel through space. Like, they become waves.
Waves, like on the ocean.
Kind of. Imagine it like this. A change in the electric field creates a magnetic field next to it. Then that changing magnetic field creates another changing electric field a little further out, and so on. And this disturbance, this pattern of changing fields, just keeps propagating outwards, like ripples spreading out from where you throw a rock in a pond.
So those ripples are what we call electromagnetic waves.
Exactly. And the source of those initial ripples, the thing that starts the whole process, is always an accelerated electric charge.
Accelerated, like speeding up or slowing down.
Yeah, any change in velocity. Because think about it, if you have a charge that's just sitting still, it creates a static electric field, no waves. But if you start shaking that charge back and forth, making it accelerate, that's when you create a changing electric field.
And that changing electric field then creates a changing magnetic field, which then creates another changing electric field, and boom, you've got a wave.
You got it. So in theory, if we could just wiggle electrons back and forth really, really fast,
We could create light, like a light bulb.
in principle, yes, because different frequencies of these waves correspond to different kinds of electromagnetic radiation. But the frequency of visible light is unbelievably high. We're talking trillions of oscillations per second.
Wow.
And the kind of wiggling we can easily do with, like, regular circuits is way, way slower.
Yeah.
That's why the first experimental confirmation of these waves was actually with radio waves.
Oh, right. Radio waves have a much lower frequency.
Right. And that was done by this guy, Heinrich Hertz, back in the late 1800s. He built devices that could actually create and detect radio waves, which was huge because it proved Maxwell's theory was right.
And, of course, we have to give shout-outs to Jagadish Chandra Bose and Guglielmo Marconi, who took this even further, especially Marconi with his, like, long-distance wireless transmissions.
Totally. They laid the foundation for all the wireless tech we have today. Now, to get a better picture of how these waves actually travel,
Yeah.
imagine the wave moving, say, to the right.
Okay, to the right.
The electric field part of the wave will be oscillating up and down, perpendicular to that direction.
Up and down. Got it.
And the magnetic field will also be oscillating, but perpendicular to both the direction of travel and the electric field. So if the electric field is going up and down, the magnetic field will be going in and out.
Oh, so they're always at right angles to each other.
Exactly. And the whole thing moves forward together like a perfectly synchronized dance. That's why we call them transverse waves. Like, if you flick a rope, the wave travels along the rope, but the rope itself is moving up and down.
Oh, yeah, I see what you mean.
And there's even, like, math equations that describe this whole wave thing. You might see stuff like E equals E naught sine of QOA minus omega t, and B equals B naught sine of QOA minus omega t.
Oh, boy, here comes the math.
Don't worry, it's not as scary as it looks. Basically, they just say that the strength of the electric and magnetic fields changes in a wave pattern as you move through space and time. The K tells you how spread out the wave is, like its wavelength, and the omega tells you how fast it's oscillating, its frequency.
And our sources mention this super important relationship. The speed of the wave, c, equals its frequency, nu, times its wavelength, lambda. So if you know how many times a wave wiggles per second and how long each wiggle is, you know how fast it's going.
And in a vacuum, the speed of these waves is always the same, and it's determined by some fundamental properties of space itself. It all boils down to this equation. C equals 1 over the square root of mu naught times epsilon naught, where mu naught and epsilon naught are these constants that describe how electric and magnetic fields behave in empty space.
And that speed, that constant c, is the speed of light.
Exactly. It's mind-blowing, right? And there's another neat relationship. The strength of the magnetic field in the wave is related to the strength of the electric field divided by the speed of light. So the electric field part of the wave is way stronger in a vacuum.
Okay, so unlike sound waves, which need, like, air or water to travel through, EM waves can go through empty space. That's how we get sunlight, right?
Totally. But when EM waves enter a different material like glass or water, their speed can change because those materials affect electric and magnetic fields differently. That's why light bends when it goes from air to water, for example.
Ah, that's why things look all wonky underwater. Okay, so we've talked about, like, the basic idea of EM waves. But what's really wild is that there's a whole spectrum of them, right?
Yeah, the electromagnetic spectrum is like a huge family of waves, all based on their frequency and wavelength. And visible light, the stuff we see, is just a tiny sliver of this whole spectrum.
So let's break it down, starting with the waves with the longest wavelengths and lowest frequencies. Our sources say those are radio waves.
Right, and we create radio waves by, like, making electrons move around in wires.
Yeah.
They're what make radio and TV broadcasts work, as well as cell phones. We're talking frequencies from hundreds of thousands to billions of cycles per second.
That's a lot of wiggling. So
Yeah.
that covers, like, AM and FM radio and all those signals our phones use, right?
Yep. Then, as we go to higher frequencies and shorter wavelengths, we hit microwaves. We use special electronic devices to generate microwaves.
Right, like in a microwave oven.
Exactly. And because they have shorter wavelengths than radio waves, they're handy for things like radar, where you bounce them off objects to detect them. And of course, in microwave ovens, we use a specific frequency of microwaves that makes water molecules vibrate really fast, generating heat and cooking our food.
Science is delicious. Okay, what's next?
Next up is infrared radiation, which we often associate with heat. Basically, anything that's warm emits infrared waves.
So, like, our bodies are emitting infrared right now.
Yep. And things like the sun, fires, even your cup of coffee.
So infrared is why those heat lamps feel so toasty.
Exactly. And our sources point out that water vapor and gases like carbon dioxide in the atmosphere are good at absorbing infrared, which is why they play a big role in the greenhouse effect, trapping heat and keeping the planet warm.
Right, the greenhouse effect. Okay, but infrared is also used for, like, practical stuff, right?
Oh, yeah. Night vision goggles use infrared, and so do those remote controls for your TV.
Okay, cool. Then after infrared, we finally hit visible light.
The good stuff. This is the only part of the spectrum that our eyes can detect. And it comes from electrons jumping between energy levels within atoms.
So, like, different jumps create different colors.
Exactly. Red light has a lower frequency than blue light, for example. And it's amazing to think that different animals have evolved to see different parts of the spectrum. Like, bees can see ultraviolet light, which helps them find flowers.
Wow, that's wild. So what's beyond violet light?
That would be ultraviolet radiation, or UV. It has even shorter wavelengths and higher energy than visible light. And it's produced by special lamps and very hot objects like the sun.
That's the stuff that gives you a sunburn.
Unfortunately, yes. Too much UV radiation can be harmful. Luckily, our planet has the ozone layer in the atmosphere, which absorbs most of the harmful UV from the sun.
Right, the ozone layer, super important. But we can also use UV for like good things, right?
Absolutely. UV light is used to sterilize medical equipment, and it's also used in some medical treatments.
So UV, helpful and harmful. Got it. What's after UV?
We're getting into the really high energy stuff now. X-rays are next, with even shorter wavelengths. We typically produce them by firing high-speed electrons at a metal target.
And X-rays are what doctors use to see inside your body, right?
Yep. They can pass through soft tissues, but not bones, which makes them super useful for medical imaging. However, they also carry a lot of energy, so it's important to limit our exposure to them.
Makes sense. And finally, at the very end of the spectrum, we have...
Gamma rays, the most energetic of them all. These are produced in nuclear reactions and radioactive decay. And because they pack so much energy, they can be dangerous. But we can also use them for good, like in cancer treatments, where they can target and destroy cancerous cells.
Wow. So we've gone from radio waves, which are all around us, to gamma rays, which are like nuclear level energy.
It's amazing, right? And while each part of the spectrum has its own unique way of being produced and detected, the fundamental nature of all these waves is the same: oscillating electric and magnetic fields traveling at the speed of light in a vacuum.
And the reason they interact with matter in such different ways is basically because of their different wavelengths and frequencies. Like radio waves can go through walls, but visible light can't.
Right. So let's wrap things up. It all started with Maxwell realizing that changing electric fields create magnetic fields, and vice versa. This crazy idea led to the prediction and discovery of electromagnetic waves, these self-sustaining ripples of energy that travel through space.
And this whole electromagnetic spectrum, from radio waves to gamma rays, is a testament to the power of those waves. They're the backbone of countless technologies, and they're constantly interacting with us and the world around us, even if we can't see them all.
And it's not just about technology. These waves are fundamental to how the universe works. They allow stars to shine, they let us communicate across vast distances, and they're even involved in the very processes that give life to our planet.
On that note, here's a little something to ponder. Think about how different animals perceive the world. Like we mentioned, bees can see ultraviolet light. Some snakes can sense infrared. They're both picking up on parts of the electromagnetic spectrum that are totally invisible to us.
It makes you wonder, what other kinds of information are out there encoded in these invisible waves? What would the world look like if we could see the full spectrum?
Mind blown. So we hope this deep dive has shed some light, pun intended, on the fascinating world of electromagnetic waves. And as always, we encourage you to keep exploring, keep asking questions, and never stop being curious about the universe around us.
And join us next time for another deep dive into the amazing world of science.
See ya.